Have you ever wondered what happens when a visitor from another star system decides to tour our cosmic neighborhood, traveling at speeds that defy imagination while performing an intricate celestial ballet around Mars? On July 1st, 2025, astronomers using the Atlas telescope in Rio Hurtado, Chile, captured something extraordinary, a faint point of light moving through space at over 200,000 kilometers per hour, carrying secrets from the depths of interstellar space. This wasn't just any space rock. The object, designated 3I/Atlas, represents only the third confirmed interstellar visitor ever detected passing through our solar system. Like a message in a cosmic bottle, it carries within its icy nucleus the chemical signatures and physical characteristics of another star system, offering us an unprecedented window into planetary formation processes that occurred billions of years ago during what astronomers call cosmic noon, the epoch when star formation peaked throughout the universe. The discovery story reads like a detective novel written in celestial mechanics. When Dr. Larry Deno and the Atlas survey team first spotted the object, catalogued initially as 11 Pli 3Z, its unusual motion immediately triggered alerts across the global astronomical community. Unlike the predictable elliptical paths of solar system natives, this visitor traced a hyperbolic trajectory, a mathematical signature that screams outsider to any astronomer who encounters it. What makes 3I/Atlas particularly fascinating is its relationship with natural systems we observe on Earth. Just as rivers carry sediments from distant mountains to the sea, interstellar objects like 3I/Atlas transport materials across the vast deserts of space between stars. The comet's nucleus, estimated to be between 440 meters and 5.6 kilometers in diameter, acts like a cosmic time capsule, preserving pristine materials from its birth star system in a frozen state for potentially billions of years. The naming convention itself tells a story of discovery and classification. The 3I indicates this is the third interstellar object confirmed by the International Astronomical Union, following 1I/Oumuamua in 2017 and 2I/Borisov in 2019. The Atlas designation honors the Asteroid Terrestrial Impact Last Alert System, a network of telescopes designed to scan the sky for potentially hazardous objects, though in this case they discovered something far more scientifically valuable than dangerous. NASA's Planetary Defense Office responded immediately to the discovery, not because 3I/Atlas posed any threat. It will pass no closer than 240 million kilometers to Earth, but because tracking interstellar objects requires precise orbital mechanics and international coordination. The office worked with telescopes in Hawaii, Chile, and Australia to refine the object's trajectory and search for precovery observations, older images that might contain the comet before its official discovery date. The search revealed observations extending back to June 14, 2025, nearly 3 weeks before the formal discovery announcement. These early images, captured by Atlas telescopes and the Zikwi Transient Facility at Palomar Observatory, provided crucial data points for calculating the object's precise orbital path and confirming its interstellar origin beyond any doubt. What truly sets 3I/Atlas apart from its interstellar predecessors is its active nature. While Oumuamua remained stubbornly inert and 2I/Borisov showed only modest cometary activity, 3I/Atlas has been putting on a spectacular show. The Hubble Space Telescope captured detailed images revealing a teardrop-shaped cocoon of dust streaming from the comet's nucleus, clear evidence of volatile materials sublimating as the ancient ice encounters our sun's warmth for the first time in eons. This activity mirrors the seasonal cycles we observe in Earth's natural world. Just as spring snow melts in mountain watersheds, creating rushing streams that carry nutrients to valleys below, 3I/Atlas is experiencing its own cosmic spring as solar radiation penetrates its surface, releasing water vapor, carbon dioxide, carbon monoxide, and even complex organic compounds into space. These materials form the comet's distinctive coma, a glowing halo of gas and dust that extends thousands of kilometers from the nucleus. The James Webb Space Telescope's infrared observations have revealed the chemical complexity of this cosmic thaw. Spectroscopic analysis has identified not just the expected water ice and carbon dioxide, but also carbonyl sulfide and various organic molecules, the building blocks of life itself. These detections suggest that 3I/ATLAS formed in a planetary system with conditions similar to those that existed in our own solar system's youth, raising profound questions about the universality of life's chemical prerequisites. As 3I/ATLAS approaches its closest encounter with Mars on October 3, 2025, at a distance of just 30 million kilometers, it offers space agencies an unprecedented opportunity to study an active interstellar comet using multiple spacecraft positioned throughout the solar system. This cosmic alignment represents a convergence of technology, timing, and scientific opportunity that may not occur again for decades. The significance of this moment extends beyond mere astronomical curiosity. Like studying the genetic diversity of migrating species to understand ecosystem health across continents, observing interstellar objects helps us comprehend the chemical and physical processes that operate across our galaxy. 3I/ATLAS carries information about stellar metallicity, planetary formation mechanisms, and the distribution of organic compounds in space, data that could revolutionize our understanding of how common Earth-like worlds might be throughout the cosmos. The comet's extraordinary speed, reaching velocities that will eventually exceed 210,000 kilometers per hour, tells us about the violence of its ejection from its birth system. Something catastrophic must have occurred to accelerate this object to such tremendous velocities, perhaps a close encounter between binary stars, the explosion of a supernova, or the gravitational slingshot effect of a massive planet. Each scenario implies different conditions in the donor star system and different probabilities for the survival and distribution of life-bearing materials across interstellar space. As we prepare to follow 3I/ATLAS on its Mars encounter, we stand at the threshold of a new era in comparative planetology, one where we can study not just objects from our own solar system, but samples of matter from alien worlds, delivered free of charge by the universe's own express delivery service. The story of 3I/ATLAS is ultimately a story about cosmic recycling, where materials forged in the hearts of ancient stars travel between worlds, potentially seeding new planetary systems with the chemical complexity necessary for life to emerge. The mathematics of 3I/ATLAS's motion tell a story that challenges our understanding of celestial mechanics and reveals the violent dynamics operating in stellar neighborhoods throughout our galaxy. Moving at approximately 137,000 miles per hour when first detected, and accelerating to over 210,000 kilometers per hour as it approaches the Sun, this interstellar wanderer exhibits speeds that place it among the fastest objects ever observed in our solar system. To understand the significance of these velocities, consider the natural world's own speed records. The fastest migrating animals on Earth, peregrine falcons in hunting dives, reach speeds of about 240 miles per hour. Arctic terns, which make the longest migrations on our planet, cruise at roughly 25 miles per hour during their pole-to-pole journeys. Yet 3I/ATLAS moves at speeds nearly 900 times faster than a diving peregrine, carrying its cargo of ancient ice and organic compounds across distances that make Arctic tern migrations seem like neighborhood strolls. The comet's hyperbolic trajectory, mathematically described by an eccentricity greater than 1.0, represents the gravitational signature of an unbound orbit. Unlike the elliptical paths that govern planets, moons, and native comets in our solar system, 3I/ATLAS follows a path that will carry it away from the Sun forever. This one-way ticket through our cosmic neighborhood results from speed so extreme that our Sun's gravity, despite its ability to hold Pluto in orbit at 40 times Earth's distance, cannot capture this interstellar visitor. The physics behind such extreme velocities point to extraordinary events in 3I/Atlas's distant past. In nature, we observe similar principles when studying explosive dispersal mechanisms, seed pods that violently rupture to scatter their contents, or volcanic eruptions that launch material at hundreds of meters per second. These terrestrial examples operate on the same fundamental physics that can accelerate interstellar objects to cosmic speeds. For 3I Atlas to achieve such velocities, several scenarios seem plausible. The most likely involves gravitational interactions with massive objects in its birth star system. Just as spacecraft use planetary flybys to gain speed, NASA's Voyager probes famously used Jupiter's gravity to reach the outer solar system. 3I/Atlas may have encountered a massive planet or stellar companion that accelerated it beyond its system's escape velocity. Another possibility involves stellar evolution events. When massive stars approach the end of their lives, they can undergo dramatic changes that affect their planetary systems. A star expanding into a red giant phase might gravitationally perturb orbiting bodies, while stellar mergers or close encounters between binary stars can completely disrupt planetary architectures. The most violent scenario involves supernova explosions, which can accelerate nearby objects to significant fractions of light speed, though such speeds would likely vaporize a comet like 3I/Atlas. The implications of studying such high-velocity interstellar objects extend far beyond curiosity about cosmic billiards. These speeds directly relate to the object's survival capabilities during its interstellar journey. The faster an object travels through space, the less time it spends exposed to cosmic radiation, interstellar dust erosion, and thermal cycling from stellar radiation fields it might encounter along its path. Like migratory animals that must navigate ocean currents, wind patterns, and seasonal changes during their journeys, 3I/Atlas has survived a multi-billion-year voyage through the Milky Way's dynamic environment. The galaxy rotates, stars move in complex patterns influenced by spiral arms and gravitational perturbations, and the comet's path would have carried it through regions of varying stellar density and radiation intensity. Recent analysis suggests that 3I/Atlas has been traveling through interstellar space for at least several billion years, possibly since the early epochs of galaxy formation, when star birth rates peaked during cosmic noon. This extended journey time means the comet has witnessed the galaxy's evolution firsthand, experiencing changes in stellar populations, metallicity gradients, and possibly even galactic collisions or interactions. The comet's approach vector provides additional clues about its origin, coming from the general direction of Sagittarius toward the galactic center, where stellar density reaches maximum values. 3I/Atlas may have originated in a region rich with massive stars and violent stellar evolution events. This crowded stellar environment increases the probability of gravitational encounters capable of ejecting planetary materials at high velocities. Observations using the Transiting Exoplanet Survey satellite TESS have revealed another intriguing characteristic. 3I/Atlas appears to be brightening faster than expected based on standard cometary models. This rapid brightening suggests either an unusually volatile rich composition or a surface structure that responds differently to solar heating than typical solar system comets. The brightening behavior mirrors seasonal phenomena we observe in Earth's ecosystems. Just as certain plants respond dramatically to the first warm days of spring, releasing stored energy in rapid growth spurts, 3I/Atlas may be experiencing its first exposure to significant stellar radiation in billions of years. The comet's surface, likely processed by cosmic rays and interstellar dust impacts during its long journey, may have developed unique physical properties that enhance its response to solar heating. This rapid evolution presents both opportunities and challenges for the upcoming Mars observations. While increased brightness makes the comet easier to detect with spacecraft instruments, it also means the object is changing rapidly. The dust and gas production that creates the observable coma also obscures the nucleus, making it difficult to determine the comet's exact size, shape, and rotation state. Advanced computer models suggest that 3I/Atlas will continue accelerating as it approaches perihelion, its closest point to the Sun, on October 29, 2025. At that moment, traveling at maximum velocity and experiencing peak solar heating, the comet will likely undergo its most dramatic transformation of the entire mission timeline. However, by that date, the geometry of planetary orbits will position the comet on the far side of the Sun from Earth, making direct observation impossible. This timing creates what mission planners call a narrow observational window, the period between now and early November when ground-based and space-based assets can study the comet before it disappears behind the Sun's glare. The Mars encounter on October 3rd represents the sweet spot in this timeline, close enough to perihelion for significant activity, but far enough from the Sun to allow detailed observation from multiple spacecraft positioned throughout the inner solar system. The speed and trajectory of 3I/Atlas also influence how spacecraft can observe it. Unlike studying nearby planets or asteroids, where spacecraft can track targets for extended periods, the comet's rapid motion requires precise timing and coordination. Each observation opportunity lasts only hours or days, demanding split-second precision in spacecraft pointing and instrument operation. This temporal compression mirrors the challenges faced by wildlife researchers studying fast-moving migratory species. Just as ornithologists must carefully time their observations to capture brief windows when rare birds pass through specific locations, mission teams must coordinate international spacecraft resources to maximize scientific return from 3I/Atlas's fleeting visit to our solar system. The date October 3rd, 2025, marks a celestial appointment that has been brewing for billions of years, the moment when interstellar comet 3I/Atlas passes within 30 million kilometers of Mars, offering humanity its closest look at a visitor from another star system. This cosmic rendezvous represents more than astronomical curiosity. It embodies the convergence of ancient wanderer and modern technology in a dance choreographed by the fundamental forces of the universe. To appreciate the significance of this approach distance, consider that 30 million kilometers places 3I/Atlas roughly 78 times farther from Mars than our Moon is from Earth. While this might seem distant by terrestrial standards, it represents an extraordinarily close encounter in astronomical terms. For comparison, when the comet reaches its closest approach to Earth later in its orbit, it will be 8 times farther away, making the Mars encounter our best opportunity for detailed study. The geometry of this approach creates optimal viewing conditions for the fleet of spacecraft currently orbiting Mars. Unlike observations from Earth, where atmospheric interference and the Sun's position can limit visibility, Mars-based observations occur in the vacuum of space with no atmospheric distortion. The orbital mechanics place multiple spacecraft in positions where they can observe 3I/Atlas against the backdrop of deep space, free from the scattered light that complicates ground-based observations. This celestial alignment mirrors the seasonal timing that governs natural migrations on Earth. Just as wildlife biologists position themselves along migration routes during peak movement periods, space agencies have spent months calculating optimal pointing strategies and instrument configurations to maximize the scientific return from this brief encounter. The difference lies in scale. While a bird migration might last weeks, 3I/Atlas will remain within optimal observation range of Mars for only a few days. The approach trajectory brings 3I/Atlas through a region of space where it will experience the combined gravitational influences of Mars, the Sun, and the asteroid belt. These multiple gravitational fields create subtle perturbations in the comet's path, tiny deflections that provide clues about its mass and internal structure. Precision tracking by Mars orbiters will measure these gravitational effects with unprecedented accuracy, potentially revealing whether the comet is a solid chunk of ancient ice or a loosely bound rubble pile held together by weak gravitational forces. The timing of this encounter coincides with increased solar activity as 3I/ATLAS continues its inward journey toward perihelion. Solar radiation pressure, which becomes stronger as objects approach the Sun, will actively push against the comet's expanding coma of gas and dust. This creates a dynamic environment where the comet's tail and coma respond in real time to changing solar conditions, a natural laboratory for studying how interstellar materials react to stellar radiation. Mars itself plays a crucial role as more than just an observation platform. The planet's thin atmosphere and lack of a strong magnetic field create conditions where solar wind particles can directly interact with any gas or dust released by 3I/ATLAS. This interaction may produce detectable effects in Mars's ionosphere or magnetosphere, potentially visible to spacecraft instruments designed to study the Martian environment. The seasonal perspective adds another layer of complexity to October observations. Mars currently experiences southern hemisphere spring, while the comet approaches from a trajectory that will carry it through the planet's orbital plane at an optimal angle for multiple spacecraft to maintain sight lines. This geometric arrangement ensures that observation opportunities won't be limited by planetary shadows or communication blackouts with Earth. Temperature dynamics during the encounter reveal the delicate balance between solar heating and radiative cooling that governs cometary evolution. As 3I/ATLAS approaches within Mars's orbital distance from the Sun, surface temperatures on the nucleus will rise above the sublimation points of various frozen gases. Water ice begins sublimating around -70 degrees Celsius, while more volatile compounds like carbon monoxide and nitrogen require even less heating to transform directly from solid to gas. These sublimation processes create the spectacular coma and tail formations visible in Hubble and Webb telescope images. The coma, a spherical cloud of gas and dust surrounding the nucleus, can extend hundreds of thousands of kilometers into space, while the tail streams away from the Sun like a cosmic windsock, indicating both solar wind direction and radiation pressure effects. For Mars orbiters, this presents both opportunity and challenge. The expanding coma makes 3I/ATLAS easier to detect and track, but also obscures the solid nucleus that contains the most primitive scientific information. Advanced image processing techniques will be essential to separate the dynamic coma from the static nucleus, requiring sophisticated algorithms that can account for the comet's rapid motion against the stellar background. The encounter geometry creates natural experiments in gravitational dynamics and orbital mechanics. As 3I/ATLAS passes through Mars' gravitational influence, its trajectory will bend slightly, a deflection measurable by precision tracking systems. This gravitational deflection, combined with observations of how solar radiation pressure affects the comet's path, will provide the most accurate mass estimate possible for this interstellar visitor. Wildlife researchers employ similar techniques when studying migrating animals using satellite telemetry. By precisely tracking movement patterns and correlating them with environmental conditions like wind patterns or ocean currents, scientists can determine behavioral adaptations and physiological constraints. The Mars encounter with 3I/ATLAS operates on identical principles, using gravitational fields instead of atmospheric or oceanic currents to reveal the comet's fundamental properties. The rapid approach velocity, over 200,000 kilometers per hour relative to Mars, compresses the observation timeline into a narrow window of opportunity. Each spacecraft will have only brief periods when 3I/ATLAS remains within instrument field of view limits, requiring precise coordination between mission control teams across multiple space agencies and countries. This temporal constraint mirrors the challenges faced by researchers studying phenomena like solar eclipses or meteor showers, where optimal observation conditions exist for only minutes or hours. The difference lies in the stakes. While a missed meteor shower will recur next year, 3I/Atlas represents a once-in-a-lifetime opportunity to study pristine materials from another star system. The October 3rd approach also coincides with seasonal dust storm activity on Mars, which could complicate atmospheric observations but might also provide unique opportunities to study interactions between interstellar dust particles and Martian atmospheric dynamics. Some mission planners speculate that dust or gas from 3I/ATLAS might temporarily interact with Mars's thin atmosphere, creating detectable changes in atmospheric composition or optical properties. As the encounter date approaches, mission teams are finalizing observation sequences that will transform this brief cosmic meeting into a treasure trove of scientific data. The success of these observations depends not only on spacecraft performance and international coordination, but also on the comet's continued evolution, as it responds to increasing solar radiation and the gravitational environment of the inner solar system. The small fleet of spacecraft currently orbiting Mars represents humanity's most sophisticated remote sensing capability, transformed from planetary explorers into impromptu astronomical observatories for the 3I/ATLAS encounter. This international armada includes NASA's Mars Reconnaissance Orbiter, Mars Odyssey, and MAVEN, ESA's Mars Express and ExoMars Trace Gas Orbiter, and the UAE's HOPE Orbiter, each bringing unique capabilities to bear on humanity's first detailed study of an active interstellar comet. The transformation of these Mars-focused missions into comet observers mirrors the adaptability we observe in natural systems. Just as migratory birds can alter their flight patterns to exploit unexpected food sources, spacecraft designed for planetary science can reprogram their instruments and observation strategies to study passing celestial objects. This flexibility represents one of the greatest triumphs of modern space exploration, the ability to respond rapidly to new scientific opportunities. Mission planners began coordinating observation strategies months in advance, recognizing that the October 3rd encounter would demand precision timing unprecedented in Mars exploration. Unlike routine planetary observations where targets remain relatively static over timescales of days or weeks, 3I/ATLAS will race across each spacecraft's field of view in hours, requiring split-second coordination between international mission control centers. The Mars Reconnaissance Orbiter, launched in 2005 and still operating at peak performance, brings the most powerful camera system to the encounter. Its high-rise, high-resolution imaging science experiment instrument, typically used to photograph Martian surface features in extraordinary detail, will attempt to capture images of 3I/ATLAS during a narrow observation window between 1-4 a.m. on October 2nd, when orbital mechanics place the spacecraft in optimal position relative to the approaching comet. HiRise's capabilities illustrate the remarkable repurposing of planetary science tools for astronomical observation. Designed to resolve objects as small as 1 meter across on the Martian surface from orbital distances of 300 kilometers, the instrument must now detect a comet nucleus potentially only hundreds of meters in diameter from distances 100,000 times greater. This challenge pushes the instrument to its absolute limits, requiring innovative observation techniques and image processing algorithms. The European Space Agency's contribution to the observation campaign exemplifies international cooperation in space science. Mars Express, ESA's veteran Mars orbiter operational since 2003, will deploy its high-resolution stereo camera HRSC in concert with its Omega and S-BICAM spectrometers. These instruments, originally designed to map Martian mineralogy and atmospheric composition, will attempt to characterize the chemical composition of 3I/ATLAS's coma and tail. Mars Express's longevity in the harsh radiation environment around Mars demonstrates the robust engineering that makes opportunistic science possible. Like a seasoned naturalist who recognizes rare species during routine wildlife surveys, this experienced spacecraft brings decades of operational expertise to the challenge of tracking a rapidly moving interstellar target. The ExoMars Trace Gas Orbiter, TGO adds cutting-edge capabilities to ESA's observation campaign. Its color and stereo surface imaging system, CASIS and NOMAD spectrometer, will work in tandem to capture both visual and spectroscopic data during the encounter. NOMAD's ability to analyze atmospheric gases in unprecedented detail, originally intended for detecting trace compounds in Mars's atmosphere, will be directed toward identifying the specific molecular species being released from 3I/ATLAS as solar heating drives sublimation processes. The UAE's HOPE orbiter represents the newest addition to the Mars fleet and brings unique capabilities to the 3I/ATLAS observation campaign. Its Emirates Mars Ultraviolet Spectrometer EMUs will attempt to detect hydrogen emissions from the comet's coma, providing direct evidence for water sublimation from the nucleus. This detection would confirm that 3I/ATLAS contains the same fundamental ingredients for life that exist throughout our solar system. HOPE's perspective offers particular advantages due to its highly elliptical orbit, which carries it much farther from Mars than the other orbiters. This extended orbit provides longer observation periods and different geometric perspectives on the comet, potentially revealing structural details invisible from closer, faster orbits around Mars. NASA's MAVEN Mars Atmosphere and Volatile Evolution spacecraft brings specialized instruments designed to study atmospheric escape processes, capabilities that prove ideal for characterizing how gas escapes from 3I/ATLAS's nucleus. MAVEN's Langmuir probe and WAVES instrument might even detect plasma interactions between the comet's ionized coma and Mars's ionosphere should the two environments intersect during the encounter. The coordination required for this multi-spacecraft observation campaign parallels the synchronized behavior observed in natural systems like flocking birds or schooling fish. Each orbiter must execute precise maneuvers to point instruments at 3I/ATLAS while maintaining communication with Earth and continuing their primary Mars science missions. Mission controllers must account for light travel time delays, spacecraft orbital mechanics, and the comet's rapidly changing position relative to each observer. Ground-based support plays a crucial role in coordinating the orbital observations. Deep Space Network antennas in California, Spain, and Australia will maintain continuous communication with the Mars fleet, relaying commands and downloading precious scientific data in real time. The coordination resembles a cosmic symphony, with conductors on Earth directing an orchestra of robotic musicians positioned around Mars. The observation strategies themselves reflect careful balance between scientific ambition and technical constraints. Each spacecraft has limited power, data storage, and communication bandwidth, forcing mission planners to prioritize the most critical measurements. Some instruments will operate continuously during the encounter, building up signal strength through repeated observations, while others will capture brief, high-resolution snapshots at precisely calculated moments. Weather conditions around Mars add another variable to observation planning. Dust storms, though less likely during the current season, could interfere with optical observations. Mission teams monitor Martian atmospheric conditions daily, ready to adjust pointing strategies or switch to different instruments if visibility degrades. The scientific return from this coordinated observation campaign will far exceed what any single spacecraft could achieve independently. By combining data from multiple vantage points, instruments, and spectral ranges, researchers will reconstruct a three-dimensional picture of 3I/ATLAS's structure, composition, and activity level during its Mars encounter. This multi-platform approach mirrors successful Earth-based research programs that combine satellite observations, aircraft measurements, and ground-based sensors to study complex environmental phenomena. The principle of convergent evidence, where multiple independent measurements support the same conclusions, will be essential for validating discoveries about this interstellar visitor. As October 3rd approaches, final preparations include rehearsal observations using known asteroids and careful calibration of instrument pointing systems. These practice runs ensure that when 3I/Atlas appears in their fields of view, the Mars orbiters will be ready to capture every possible detail of this remarkable interstellar encounter. The success of this international coordination effort will establish precedents for future multi-spacecraft observations of rare astronomical phenomena, demonstrating humanity's growing capability to transform existing space assets into powerful tools for exploring unexpected discoveries throughout the solar system. The European Space Agency's two-spacecraft observation campaign represents a masterclass in adaptive mission planning, where decades-old Mars Express joins forces with the cutting-edge ExoMars Trace Gas Orbiter to create a powerful interstellar comet detection system. This collaboration exemplifies how space agencies maximize scientific return by leveraging complementary capabilities across multiple missions, much like how different species in an ecosystem fill specialized niches while contributing to the overall health of their environment. Mars Express, launched in 2003 and now in its 22nd year of operations, brings the wisdom of experience to the 3I/Atlas encounter. This veteran spacecraft has survived solar storms, equipment failures, and the gradual degradation that affects all electronic systems in space, yet continues to perform cutting-edge science with remarkable reliability. Like an experienced tracker reading subtle signs in the wilderness, Mars Express has learned to extract maximum information from minimal resources. The spacecraft's high-resolution stereo camera, HRSC, will be tasked with capturing images of 3I/Atlas during the October 3rd approach, despite being designed for entirely different purposes. Originally intended to create detailed topographical maps of Mars by photographing surface features from multiple angles, HRSC must now detect and track a small, rapidly moving object against the star field. This represents a fundamental shift from mapping static terrain to pursuing dynamic targets, analogous to a landscape photographer suddenly switching to wildlife photography of fast-moving subjects. HRSC's 9 charge-coupled device CCD sensors, arranged in a linear array, normally build up detailed images as the spacecraft orbits Mars and the planet's surface scrolls beneath the camera. For 3I/ATLAS observations, mission planners have developed new software that allows the camera to track the comet's motion, essentially turning the entire instrument into a sophisticated astronomical telescope. This adaptation required months of programming work and extensive testing to ensure the modified software wouldn't interfere with ongoing Mars mapping operations. The technical challenges of photographing 3I/Atlas with HRSC mirror those faced by wildlife photographers attempting to capture images of rare, fast-moving animals. The comet's rapid apparent motion across the sky requires precise timing and tracking, while its relatively faint brightness demands long exposure times that must be balanced against the risk of motion blur. Mission controllers have calculated optimal observation windows when Mars Express's orbital position provides the best combination of comet visibility and spacecraft stability. Mars Express's Omega Observatoire pour la minéralogie, l'eau, les glaces et l'activité spectrometer adds crucial compositional analysis capabilities to the observation campaign. This instrument, which normally identifies minerals on the Martian surface by analyzing reflected sunlight, will be redirected to study the light emitted and reflected by 3I/ATLAS, coma, and tail. Omega's ability to simultaneously measure hundreds of different wavelengths makes it ideal for detecting the spectral signatures of various molecules being released from the comet's nucleus. The spectroscopic analysis planned by Omega resembles the work of forensic investigators using chemical analysis to identify unknown substances. Each molecule absorbs and emits light at characteristic wavelengths, creating unique spectral fingerprints that reveal composition and physical conditions. For 3I/Atlas, Omega will search for signatures of water vapor, carbon dioxide, carbon monoxide, and more complex organic compounds, the building blocks of life that may be common throughout the galaxy. SPECM spectroscopy for investigation of characteristics of the atmosphere of Mars represents Mars Express's third major contribution to the comet observation campaign. This ultraviolet spectrometer, normally used to study Mars's upper atmosphere, will attempt to detect hydrogen emissions from 3I/Atlas's coma. Hydrogen emission provides direct evidence for water sublimation, as solar ultraviolet radiation breaks apart water molecules and causes hydrogen atoms to glow at specific wavelengths. The ExoMars Trace Gas Orbiter brings 21 stationary technology to complement Mars Express's proven capabilities. Launched in 2016, TGO represents ESA's most advanced Mars orbiter, equipped with instruments capable of detecting atmospheric gases at concentrations measured in parts per billion. This extraordinary sensitivity, originally designed to search for methane and other potential biosignatures in Mars's atmosphere, will be focused on the much brighter and more abundant gases surrounding 3I/Atlas. TGO's color and stereo surface imaging system CASIS offers higher resolution and more sophisticated image processing capabilities than HRSC, though both cameras face similar challenges in tracking the rapidly moving comet. CASIS's ability to capture stereoscopic image pairs, two slightly different views of the same target, could potentially reveal three-dimensional structure in 3I/Atlas's coma or tail, providing insights into how gas and dust are distributed around the nucleus. The NOMAD, Nadir and Occultation for Mars Discovery Spectrometer represents TGO's premier scientific instrument and the most sophisticated tool available for analyzing 3I/ATLS's composition. NOMAD combines three separate spectrometer channels covering ultraviolet, visible, and infrared wavelengths, allowing simultaneous analysis across a broad range of the electromagnetic spectrum. This comprehensive spectral coverage is essential for identifying the full range of molecules that might be present in the comet's coma. NOMAD's extraordinary sensitivity stems from its ability to perform solar occultation measurements, observations where it analyzes sunlight passing through Mars's atmosphere, or in this case, 3I/ATLS's coma, to detect absorption by trace gases. This technique can identify molecular species at concentrations thousands of times lower than direct emission spectroscopy, potentially revealing rare or unexpected compounds in the interstellar visitor's composition. The coordination between Mars Express and TGO requires precise synchronization of observation schedules, data collection protocols, and communication with Earth. Both spacecraft must simultaneously point at 3I/Atlas, while maintaining their primary Mars science operations and regular communications schedules with ground controllers. This juggling act resembles a complex dance where each performer must execute precise movements while staying in harmony with their partner. Mission planners have identified several critical observation windows when both spacecraft can simultaneously view 3I/Atlas from different orbital positions around Mars. These coordinated observations will provide stereo viewing angles that could reveal three-dimensional structure in the comet's coma and tail, while simultaneous spectroscopic measurements will help validate compositional analyses and account for temporal variations in gas production. The data processing challenges for ESA's dual spacecraft campaign require innovative approaches to combine information from instruments with different capabilities, calibrations, and observational geometries. Scientists must account for the different flight paths, pointing accuracies, and instrumental responses of each spacecraft while extracting maximum scientific value from potentially brief observation periods. Ground-based support for the ESA campaign utilizes the agency's deep space communication network, including stations in Spain and Australia, to maintain continuous contact with both spacecraft during the critical observation periods. Real-time monitoring allows mission controllers to adjust pointing strategies or switch between instruments if initial observations reveal unexpected phenomena or technical issues. The success of ESA's coordinated observation campaign will demonstrate the agency's growing expertise in multi-mission operations and adaptive science planning. Beyond the immediate scientific return from studying 3I/Atlas, This campaign serves as a proving ground for future coordinated observations of rare astronomical events, potentially including other interstellar objects, unusual asteroids, or time-sensitive phenomena throughout the solar system. The European approach to the 3I/Atlas encounter emphasizes the value of international cooperation and long-term investment in space science infrastructure. By maintaining operational spacecraft for decades and continually upgrading their capabilities, ESA has created opportunities to study phenomena that couldn't have been anticipated when these missions were originally designed and launched. NASA's response to the 3I/Atlas encounter demonstrates the agency's unparalleled ability to coordinate resources across multiple missions, transforming a diverse fleet of spacecraft into a unified observation network spanning from Earth orbit to the outer solar system. This coordinated campaign represents the largest multi-mission astronomical observation ever attempted, involving assets originally designed for planetary exploration, astrophysics, and solar research. The scope of NASA's 3I/Atlas campaign reads like an inventory of American space exploration achievements over the past 2 decades. The Hubble Space Telescope, operational since 1990, provides the highest resolution images of the comet's nucleus and coma structure. The James Webb Space Telescope contributes unprecedented infrared spectroscopy, revealing the chemical composition of gases being released from the ancient ice. Mars orbiting assets, including the Mars Reconnaissance Orbiter and Curiosity rover, add ground truth perspectives from the red planet's vicinity. This multi-platform approach mirrors the redundancy and specialization found in healthy ecosystems, where different species fill complementary roles while providing backup capabilities for essential functions. Each NASA spacecraft brings unique capabilities to the 3I/Atlas study, while overlapping observations provide the redundancy necessary to validate discoveries and account for instrumental limitations or unexpected failures. The Hubble Space Telescope's contribution to the campaign leverages nearly 35 years of operational experience in precision pointing and astronomical observation. Hubble's Advanced Camera for Surveys and Wide-Field Camera 3 have captured the sharpest images of 3I/Atlas available from any source, revealing the teardrop-shaped coma and nascent tail structure that confirm the object's cometary nature. These observations required innovative tracking techniques, as Hubble was never designed to follow rapidly moving objects across its field of view. Hubble's observations have revealed crucial details about 3I/Atlas's activity level and nucleus size. By analyzing the brightness distribution within the coma and measuring how light scatters off dust particles, astronomers have constrained the nucleus diameter to between 440 meters and 5.6 kilometers. This size range places 3I/Atlas among the smaller interstellar objects detected to date, yet its high activity level suggests either an unusually volatile rich composition or unique surface properties developed during its interstellar journey. The James Webb Space Telescope brings revolutionary infrared capabilities to the study of 3I/Atlas, operating in wavelength regions where many important molecular species emit characteristic signatures. Webb's near-infrared spectrograph has detected water vapor, carbon dioxide, carbon monoxide, and carbonyl sulfide in the comet's coma, direct confirmation that this interstellar visitor contains the same basic ingredients found in solar system comets. Webb's observations represent a breakthrough in interstellar object science, providing the first detailed chemical analysis of gases released from an active interstellar comet. The detected molecules suggest that 3I/Atlas formed in an environment similar to our outer solar system, where temperatures were low enough to preserve volatile compounds as solid ice for billions of years. This chemical similarity raises profound questions about the universality of planetary formation processes throughout the galaxy. The SPHEREX spectrophotometer for the history of the universe, Epoch of Regionization and ICE's Explorer mission, launched in 2024, provides complementary infrared observations that extend Webb's spectroscopic coverage across broader wavelength ranges. SPHEREX's all-sky survey capabilities allow it to track 3I/8LS continuously as the comet moves across different portions of the sky, providing temporal coverage impossible with pointing-limited telescopes. NASA's Mars Reconnaissance Orbiter, MRO, occupies a unique position in the observation campaign, stationed near Mars during the comet's closest approach on October 3rd. MRO's high-rise camera will attempt to capture the highest resolution images possible of 3I/Atlas from any spacecraft, though the 30 million kilometer distance will limit resolution to approximately 30 kilometers per pixel. Despite this limitation, high-rise observations could reveal large-scale structure in the comet's coma or detect fragmentation events if the nucleus breaks apart under tidal stress. The Mars Sample Return mission elements, including the Perseverance rover and Ingenuity helicopter, add surface-based perspectives to the observation campaign, while their primary mission focuses on collecting and analyzing Martian rock samples. Both assets carry cameras and spectrometers capable of detecting 3I/Atlas if atmospheric conditions permit. These observations would provide the first ground-based views of an interstellar comet from another planet's surface. NASA's coordination of the 3I/Atlas campaign extends beyond Earth orbit to include deep space missions currently en route to their primary targets. The Europa Clipper spacecraft, launched in 2024 and currently traveling toward Jupiter, will attempt observations during its cruise phase, while the Lucy mission, designed to study Trojan asteroids, may capture images during its outbound trajectory. The Psyche mission represents a particularly intriguing element of the Deep Space Observation Network. This spacecraft, en route to study a metal-rich asteroid in the main belt, passed within 0.302 AU of 3I/Atlas on September 4, 2025. While no official images have been released, this close approach likely provided the best direct observation of the comet from any spacecraft, potentially revealing details about nucleus rotation, surface features, or localized gas production that remain invisible from greater distances. Parker Solar Probe, NASA's closest approach mission to the Sun, adds a unique solar physics perspective to 3I/Atlas observations. As the comet approaches perihelion and experiences maximum solar heating, Parker's instruments will monitor solar wind conditions and electromagnetic field variations that might interact with the comet's expanding coma and tail. These observations could reveal how interstellar comets respond to the extreme environments near their host stars. The TESS, Transiting Exoplanet Survey Satellite Mission, contributes long-term monitoring capabilities to the 3I/ATLAS campaign. TESS's precision photometry, originally designed to detect planetary transits across distant stars, can measure subtle brightness variations in the comet as it rotates and responds to changing solar illumination. These measurements provide insights into nucleus shape, rotation period, and activity patterns that complement the higher resolution observations from other platforms. Ground-based support for NASA's multi-mission campaign utilizes the Deep Space Network's 3 complexes in California, Spain, and Australia to maintain continuous communication with participating spacecraft. The coordination challenges resemble air traffic control for cosmic investigations, with mission controllers scheduling observation sequences, data downloads, and trajectory corrections for multiple spacecraft simultaneously. The data fusion challenges for NASA's campaign require sophisticated algorithms to combine observations across different wavelengths, resolutions, and viewing geometries. Machine learning techniques are being employed to identify subtle patterns in the combined dataset that might escape detection in individual observations. This approach mirrors ecological research methods, where scientists combine satellite imagery, ground surveys, and environmental sensors to understand complex ecosystem dynamics. Real-time coordination allows NASA mission teams to adapt observation strategies based on preliminary results from other spacecraft. If Hubble detects unexpected brightness variations, Webb can be redirected to perform detailed spectroscopy of specific regions. If Mars orbiters identify unusual activity patterns, deep space missions can extend their observation periods to capture long-term evolution. The success of NASA's coordinated 3I/Atlas campaign will establish new paradigms for multi-mission space science, demonstrating how agencies can leverage existing assets to study unexpected phenomena. This capability becomes increasingly important as more interstellar objects are discovered and as the pace of astronomical discovery accelerates with next-generation survey telescopes coming online. Beyond immediate scientific return, the 3I/Atlas campaign serves as a proof of concept for rapid response astronomical observation using distributed space assets. This capability could prove crucial for studying time-sensitive phenomena like supernovae, gravitational wave sources, or future interstellar visitors that provide only brief observation windows. The United Arab Emirates HOPE spacecraft represents one of the most remarkable success stories in modern space exploration, transforming from an ambitious national project into a crucial contributor to humanity's first detailed study of an interstellar comet. Launched in 2020 as the Emirates Mars mission, HOPE's unique orbital characteristics and advanced instrumentation make it an invaluable asset for observing 3I/ATLAS during its October encounter with the Red Planet. HOPE's elliptical orbit around Mars provides advantages unavailable to any other spacecraft in the current fleet observing 3I/ATLAS. While most Mars orbiters follow relatively circular paths that keep them close to the planet, HOPE's elongated orbit carries it as far as 43,000 kilometers from Mars, nearly 10 times farther than typical orbits. This extended range offers longer observation periods and unique geometric perspectives on the approaching comet. The orbital mechanics create natural observation windows that complement rather than compete with other spacecraft, while close-orbiting craft have brief opportunities to observe 3I/ATLAS as it races across their limited fields of view. HOPE can maintain sightlines for extended periods, tracking the comet's evolution over hours rather than minutes. This temporal advantage mirrors the patient observation strategies employed by wildlife researchers studying migratory animals, where sustained monitoring reveals behavioral patterns invisible during brief encounters. HOPE's Emirates Mars Ultraviolet Spectrometer, EMUS, represents the mission's most significant contribution to 3I/ATLAS science. This sophisticated instrument operates in wavelength ranges where many important atomic and molecular species emit characteristic signatures, particularly hydrogen, the smoking gun for water sublimation from cometary nuclei. EMUS was originally designed to study how Mars loses its atmosphere to space, tracking hydrogen atoms as they escape the planet's gravitational pull and disperse into the solar wind. The adaptation of EMUS for comet observation required innovative pointing strategies and software modifications. Unlike Mars atmospheric observations, which target predictable phenomena occurring continuously above the planet, 3I/ATLAS observations demand precise tracking of a rapidly moving point source. Mission engineers have developed new pointing algorithms that allow EMUS to follow the comet's trajectory while maintaining the instrument stability necessary for sensitive ultraviolet measurements. Ultraviolet spectroscopy reveals processes invisible to human eyes and conventional cameras. When solar ultraviolet radiation strikes water molecules in 3I/ATLAS's coma, it breaks the chemical bonds and creates free hydrogen atoms that emit light at specific wavelengths. This phenomenon, called photodissociation, produces a glowing hydrogen cloud around the comet that extends far beyond the visible coma. EMUs can detect this extended hydrogen envelope, providing direct evidence for water content even when other instruments cannot resolve the comet's nucleus. The scientific significance of hydrogen detection extends beyond confirming water presence. The intensity and spatial distribution of hydrogen emissions reveal information about water sublimation rates, nucleus rotation effects, and seasonal variations in activity. like reading the smoke patterns from a distant fire to understand wind conditions and fuel types. EMES observations of hydrogen distribution around 3I/Atlas will reveal the physical processes governing gas release from interstellar cometary materials. HOPE's contribution to the International Observation Campaign exemplifies the democratizing effect of modern space technology. The UAE's space program, established less than 2 decades ago, now operates instruments capable of making discoveries impossible for ground-based telescopes or many other space missions. This achievement demonstrates how emerging spacefaring nations can contribute meaningfully to global scientific endeavors through focused investment in specific capabilities. The Emirates Mars mission's success story parallels natural examples of specialized adaptation, where organisms develop unique capabilities that allow them to exploit ecological niches unavailable to competitors. HOPE's specialized orbit and ultraviolet capabilities fill a scientific niche that complements rather than duplicates the work being performed by other Mars orbiters, maximizing the overall return from the International Observation Campaign. EMU's observations during the 3I/Atlas encounter will also advance understanding of how solar wind conditions affect cometary activity. The instrument's sensitivity to charged particle interactions allows it to monitor how Mars's magnetosphere and ionosphere respond to gas and plasma streaming away from the comet. These interactions might produce detectable auroral emissions or magnetic field perturbations that provide insights into the comet's plasma environment. The technical challenges of ultraviolet astronomy from Mars orbit include accounting for scattered sunlight, cosmic ray interference, and instrument degradation from prolonged space exposure. EMUs incorporate sophisticated calibration systems and background subtraction algorithms that allow it to detect faint spectral features against the bright ultraviolet background of solar radiation scattered by interplanetary dust. Coordination with other spacecraft observations requires precise timing to maximize scientific synergy. When EMUS detects hydrogen emissions from 3I/Atlas, simultaneous visible light observations by Mars Express or ExoMars TGO can correlate these emissions with dust and gas production visible in conventional images. This multi-wavelength approach provides comprehensive understanding of the physical and chemical processes occurring as the ancient interstellar ice responds to solar heating. HOPE's data processing and analysis capabilities reflect the UAE's investment in developing indigenous space science expertise. The Emirates Mars mission's science team includes researchers from universities and institutes across the UAE, working in collaboration with international partners to extract maximum scientific value from EMU's observations. This approach ensures that the UAE maintains ownership of its contributions to 3I/Atlas science while participating fully in the global research community. The mission's communication systems utilize NASA's Deep Space Network to maintain contact with Earth, demonstrating how international cooperation in space infrastructure enables scientific achievements that would be impossible for individual nations operating independently. HOPE's data streams will be integrated with observations from ESA and NASA spacecraft to create comprehensive models of 3I/Atlas's structure and activity. Beyond the immediate scientific return from 3I/Atlas observations, HOPE's participation in the international campaign establishes precedents for future cooperative space science missions. The UAE's success demonstrates how smaller spacefaring nations can leverage targeted investments and international partnerships to make significant contributions to fundamental research questions about the universe. The cultural significance of the HOPE mission extends beyond technical achievements to represent the UAE's commitment to scientific excellence and international collaboration. The spacecraft's name embodies aspirations for peaceful space exploration and knowledge sharing that transcend national boundaries, principles exemplified by the coordinated international response to 3I/Atlas's visit to our solar system. Educational outreach associated with HOPE's 3I/Atlas observations will inspire the next generation of space scientists and engineers throughout the Arab world. The mission demonstrates how space exploration can serve as a catalyst for technological development and scientific education, creating capabilities that benefit society long after specific missions conclude. Real-time data sharing protocols allow HOPE's EMU's observations to inform targeting decisions by other spacecraft in the Mars fleet. If ultraviolet observations reveal unexpected activity patterns or previously undetected gas species, mission controllers can redirect other instruments to perform complementary measurements. This responsive coordination maximizes the scientific return from the brief observation window available during 3I/Atlas's Mars encounter. The success of HOPE's contribution to 3I/Atlas science will validate the UAE's strategic approach to space exploration, which emphasizes developing specific technical capabilities that address important scientific questions while building sustainable national expertise in space technology and operations. The Mars Reconnaissance Orbiter's HiRISE, high-resolution imaging science experiment, camera faces perhaps its most challenging assignment since beginning operations in 2006, capturing detailed images of 3I/Atlas during a narrow 4-hour window between 1 o'clock and 4 a.m. on October 2, 2025. This observation attempt will push the instrument to its absolute limits, requiring unprecedented precision in spacecraft pointing and timing to photograph an object moving at over 200,000 kilometers per hour from a distance of 30 million kilometers. HiRISE represents one of the most powerful cameras ever flown in space, capable of resolving objects as small as 1 meter across on the Martian surface from orbital altitudes of 250 meters (300 kilometers). This extraordinary resolution stems from its 0.5-meter primary mirror, the largest telescope mirror ever sent to another planet, combined with sophisticated CCD detectors and precision pointing systems. However, the 3I/Atlas observation will test capabilities far beyond the instrument's original design parameters. The technical challenges of photographing 3I/Atlas with HiRISE resemble those faced by wildlife photographers attempting to capture images of fast-moving, distant subjects under challenging lighting conditions. The comet's rapid apparent motion across the sky requires precise tracking algorithms, while its relatively faint brightness demands long exposure times that must be balanced against the risk of motion blur. Mission controllers have spent months developing specialized pointing sequences that allow HiRISE to follow the comet's predicted trajectory with unprecedented accuracy. The observation geometry places extraordinary demands on the Mars Reconnaissance Orbiter's attitude control system. Unlike routine Mars surface imaging, where the spacecraft can rely on the planet's gravitational field for stable pointing reference, tracking 3I/Atlas requires pointing toward empty space while maintaining precise orientation relative to distant stars. The spacecraft must execute complex maneuvers that account for its orbital motion around Mars, the comet's rapid movement through the solar system, and the gravitational perturbations affecting both objects. From HiRISE's perspective at the time of observation, 3I/Atlas will appear as a faint star-like object moving against the background of distant stars. The comet's nucleus, the solid ice and rock component that contains the most scientifically valuable information, will likely remain unresolved even at HiRISE's maximum resolution. However, the instrument should be capable of detecting and characterizing the comet's coma and potentially its developing tail, providing crucial information about gas and dust production rates. The pixel scale during the 3I/Atlas observation will be approximately 30 kilometers per pixel, vastly different from HiRISE's typical Mars surface resolution of less than 1 meter per pixel. This dramatic change in scale requires specialized image processing techniques and careful calibration to extract meaningful scientific information. Mission scientists have developed new analysis algorithms specifically for this observation, drawing on techniques used in astronomical image processing and adapting them for HiRISE's unique characteristics. Color imaging capabilities add another dimension to the planned high-rise observations. The instrument's red, blue-green, and near-infrared filters can reveal information about the size, distribution, and composition of dust particles in 3I/ATLS's coma. Different particle sizes scatter light differently at various wavelengths, creating color variations that provide clues about the physical processes occurring as the comet's nucleus responds to solar heating. The timing of the October 2nd observation window reflects careful calculations of orbital mechanics and optimal viewing geometry. During this period, the Mars Reconnaissance Orbiter will be positioned in its orbit where Earth communications are possible while maintaining optimal sightlines to 3I/ATLS. The spacecraft's solar arrays will be oriented to provide maximum power. Atmospheric conditions around Mars could potentially interfere with the high-rise observations, though the probability of significant dust storm activity remains low during the current Martian season. Mission planners monitor Martian weather patterns continuously, prepared to adjust observation strategies if atmospheric opacity increases unexpectedly. The instrument's multiple color filters provide some capability to compensate for atmospheric effects, similar to how ground-based astronomers use different wavelengths to peer through Earth's atmosphere. The data processing pipeline for HiRise's 3I/ATLS images will require innovative techniques to separate the comet's signal from background noise and cosmic ray hits. Unlike Mars surface images, where features remain static between exposures, the comet's motion creates unique challenges for standard noise reduction algorithms. Mission scientists are developing specialized processing methods that account for the comet's predicted motion while preserving the subtle brightness variations that contain scientific information. Comparison with ground-based telescopic observations provides crucial validation for high-rise results. While the spacecraft-based observations offer superior resolution and freedom from atmospheric interference, ground-based telescopes can provide simultaneous observations that help calibrate high-rise measurements and account for temporal variations in the comet's activity. This multi-platform approach ensures that discoveries made during the brief observation window can be properly contextualized and validated. The scientific goals for HiRise's 3I/ATLAS observation include measuring the comet's brightness and color variations, detecting any structure within the coma, and searching for evidence of fragmentation or jets of material streaming from specific locations on the nucleus. These measurements will provide ground truth for models of cometary activity and help calibrate observations made by other spacecraft in the Mars fleet. Engineering considerations for the observation include managing spacecraft power, thermal conditions, and data storage limitations during the extended pointing sequence required to track 3I/ATLS. The Mars Reconnaissance Orbiter must maintain communication with Earth while executing precise maneuvers requiring careful coordination between attitude control, power management, and communication systems. The legacy significance of HiRise's 3I/ATLS observations extends beyond immediate scientific return to demonstrate the adaptability and longevity of well-designed space instruments. Nearly 2 decades after launch, HiRise continues to push the boundaries of planetary imaging while taking on completely new challenges that its designers never anticipated. This capability represents one of the greatest returns on investment in space exploration, instruments that continue producing groundbreaking science long after their primary missions conclude. Real-time monitoring during the observation sequence allows mission controllers to make fine adjustments to pointing accuracy and exposure parameters based on initial results. If the comet appears brighter or fainter than predicted, observation strategies can be modified in real time to optimize scientific return. This adaptive approach maximizes the probability of success during the brief window when optimal viewing conditions exist. Success criteria for the HiRise observation include detecting 3I/ATLAS against the stellar background, measuring its brightness accurately, and potentially resolving structure within the comet's coma. Even a marginal detection would provide valuable constraints on the comet's size and activity level, while a successful high-quality image could reveal details about interstellar cometary processes visible nowhere else. The coordination between high-rise observations and simultaneous measurements by other Mars orbiters will create a comprehensive snapshot of 3I/ATLAS during its closest approach to Mars. This coordinated campaign represents the most detailed study of an interstellar comet ever attempted, leveraging humanity's entire Mars exploration infrastructure to study a visitor from another star system. The international fleet of spacecraft orbiting Mars brings together the most sophisticated array of scientific instruments ever assembled for studying an interstellar object, creating a virtual observatory that spans multiple wavelengths, measurement techniques, and observational perspectives. This convergence of technologies represents decades of advancement in space instrumentation, from pioneering devices launched in the early 2000s to cutting-edge sensors incorporating the latest developments in detector technology and digital signal processing. The spectroscopic arsenal deployed against 3I/ATLAS reads like a comprehensive survey of modern analytical chemistry techniques adapted for space exploration. Mars Express carries the Omega Observatoire pour la minéralogie, l'eau, les glaces et l'activité imaging spectrometer, which combines spatial imaging with spectral analysis across visible and near-infrared wavelengths. This instrument, operating since 2004, has proven remarkably durable and continues to deliver science-quality data nearly 2 decades after launch. Omega's contribution to 3I/ATLAS observations leverages its unique capability to simultaneously map spatial structure and spectral characteristics across hundreds of wavelengths. Originally designed to identify minerals on the Martian surface by analyzing how different compounds absorb and reflect sunlight, Omega will be redirected to study how gases in the comet's coma emit and absorb radiation. This technique mirrors the work of forensic investigators using spectral analysis to identify unknown substances, where each molecular species leaves distinctive fingerprints across the electromagnetic spectrum. The ExoMars Trace Gas Orbiter's NOMAD, Nadir and Occultation for Mars Discovery Spectrometer represents the current state-of-the-art in space-based atmospheric analysis. This sophisticated instrument combines 3 separate spectrometer channels: ultraviolet, visible, near-infrared, and thermal infrared, allowing simultaneous analysis across wavelength regions where different molecular species exhibit their strongest spectral features. NOMAD's extraordinary sensitivity, capable of detecting trace gases at concentrations measured in parts per billion, will be focused on the much brighter emissions from 3I/ATLAS's active coma. The complementary nature of these spectroscopic capabilities creates a comprehensive analytical laboratory for studying interstellar cometary composition. Different molecular species exhibit their strongest spectral features at different wavelengths. Water vapor shows distinctive absorption bands in the near-infrared. Carbon dioxide has strong features in the thermal infrared, while various organic compounds create complex signatures across multiple wavelength regions. By combining observations from multiple spectrometers, scientists can build complete inventories of the gases being released from 3I/ATLAS's ancient nucleus. Camera systems add crucial spatial information to complement the chemical analysis provided by spectrometers. The high-resolution stereo camera, HRS-C aboard Mars Express, and the color and stereo surface imaging system, CASIS, on the ExoMars Trace Gas Orbiter will attempt to resolve structure within 3I/ATLAS's coma and tail. These instruments face the unique challenge of photographing a small, rapidly moving object from distances thousands of times greater than their typical planetary observation ranges. The technical adaptations required to repurpose planetary cameras for astronomical observation mirror the versatility demonstrated by professional photographers who modify their equipment and techniques to capture different types of subjects. Camera systems designed for high-resolution planetary mapping must be reconfigured for tracking moving targets against stellar backgrounds, requiring new pointing algorithms, exposure strategies, and image processing techniques. Mars Reconnaissance Orbiter's HiRISE camera brings unparalleled resolution to the observation campaign, though even its powerful optics will be stretched to their limits. The instrument's 0.5-meter primary mirror and advanced CCD detectors, normally capable of resolving meter-scale features on Mars, will attempt to detect structure within 3I/ATLAS's coma at pixel scales of approximately 30 kilometers. This dramatic change in observational scale requires careful calibration and specialized image processing to extract meaningful scientific information. The UAE's HOPE spacecraft contributes unique ultraviolet spectroscopic capabilities through its Emirates Mars Ultraviolet Spectrometer (EMUs). This instrument operates in wavelength regions where hydrogen atoms, the photodissociation products of water molecules, emit characteristic signatures. EMU's observations can detect extended hydrogen clouds around 3I/ATLAS that extend far beyond the visible coma, providing direct evidence for water sublimation rates and spatial distribution. Ultraviolet spectroscopy reveals processes invisible to conventional optical observations, much like how specialized lighting techniques in biological research reveal cellular structures invisible under normal illumination. The hydrogen envelopes surrounding active comets can extend millions of kilometers from the nucleus, creating a vast reservoir of information about water content and sublimation processes that remains undetectable at visible wavelengths. The coordination of simultaneous observations across multiple instruments and spacecraft creates unprecedented opportunities for cross-validation and comprehensive analysis. When NOMAD detects carbon dioxide emissions from specific regions of 3I/ATLAS's coma, simultaneous imaging by CASIS or HRSE can correlate these emissions with visible dust jets or structural features. This multi-instrument approach provides the redundancy necessary to confirm discoveries and the comprehensive coverage needed to understand complex physical processes. Data fusion techniques combine observations from different instruments to create unified models of 3I/ATLAS's structure and activity. Machine learning algorithms are being developed to identify subtle correlations between spectroscopic measurements and imaging data that might escape detection through traditional analysis methods. These computational approaches mirror techniques used in medical imaging where multiple diagnostic methods are combined to create comprehensive pictures of complex systems. Real-time coordination between instruments allows adaptive observation strategies that respond to discoveries made during the encounter. If spectroscopic observations reveal unexpected molecular species or unusually high activity levels, imaging systems can be redirected to search for the spatial sources of these phenomena. This responsive approach maximizes scientific return from the brief observation windows available during 3I/ATLAS's rapid passage through the inner solar system. The temporal aspects of multi-instrument observations provide insights into the dynamic evolution of cometary activity. Comets are not static objects, but respond continuously to changing solar radiation, internal pressure variations, and rotational effects. By coordinating observations across multiple instruments, scientists can track how 3I/ATLAS's coma and tail evolve in real time as the nucleus rotates and different surface regions experience varying degrees of solar heating. Calibration challenges for multi-instrument campaigns require careful accounting of differences in spectral resolution, sensitivity, and observational geometry between various spacecraft and instruments. Each instrument has unique characteristics that must be considered when combining data. NOMAD operates at higher spectral resolution than Omega, while camera systems provide spatial information unavailable from point source spectrometers. Sophisticated calibration procedures ensure that measurements from different sources can be meaningfully compared and combined. The technological legacy of the 3I/ATLAS observation campaign extends beyond immediate scientific return to advance the state of the art in multi-platform space science. The coordination techniques, data fusion algorithms, and real-time adaptive strategies developed for this campaign will enable future studies of rare astronomical phenomena requiring rapid response and international cooperation. Error analysis and uncertainty quantification become particularly important when combining data from multiple sources with different instrumental characteristics and calibration histories. Bayesian statistical methods are being employed to properly account for measurement uncertainties while extracting maximum information from the combined dataset. These techniques ensure that discoveries claimed based on multi-instrument observations can withstand rigorous scientific scrutiny. The scientific return from convergent observations will far exceed what any single instrument could achieve independently. By combining spectroscopic identification of molecular species with spatial mapping of their distribution, scientists will create three-dimensional models of 3I/Atlas's activity that reveal the physical processes governing gas release from interstellar cometary materials. This comprehensive understanding represents a breakthrough in comparative planetology, extending our knowledge beyond objects native to our solar system to include samples of matter from alien worlds delivered by cosmic processes operating throughout the galaxy. While the Mars orbital fleet captures headlines for their front-row seats to 3I/Atlas's October encounter, a network of deep space missions scattered throughout the solar system will provide equally valuable perspectives on this interstellar visitor. These distant observers, originally launched for entirely different scientific missions, now find themselves perfectly positioned to study the comet from unique vantage points that complement the Mars-centered observations and extend our understanding of how 3I/Atlas behaves across different regions of the inner solar system. The European Space Agency's JUICE, Jupiter Icy Moons Explorer spacecraft, occupies perhaps the most intriguing position in this extended observation network. Launched in 2023 and currently cruising toward Jupiter, JUICE will attempt observations of 3I/Atlas in November 2025 using its sophisticated array of cameras, spectrometers, and particle sensors. The spacecraft's location provides a perspective unavailable to any Earth-based or Mars-based observer, potentially revealing aspects of the comet's activity that remain invisible from other viewing angles. JUICE's observational capabilities reflect the cutting-edge technology intended for studying Jupiter's icy moons Europa, Ganymede, and Callisto. The spacecraft carries multiple camera systems designed to photograph surface features on these distant worlds, spectrometers for analyzing their thin atmospheres and surface compositions, and particle detectors for studying their interaction with Jupiter's powerful magnetosphere. These same instruments can be redirected to study 3I/Atlas, creating opportunities for discoveries impossible from any other platform. The temporal aspects of JUICE's planned observations provide unique scientific value. By November 2025, 3I/Atlas will have passed through perihelion, its closest approach to the Sun, and begun its journey back toward interstellar space. JUICE observations will capture the comet in a post-perihelion state, when maximum solar heating has triggered peak activity levels, potentially revealing structural changes or fragmentation events invisible during the earlier Mars encounter. Coordination between JUICE and NASA's Europa Clipper mission creates possibilities for stereoscopic observations of 3I/Atlas from two different deep space perspectives. Both spacecraft carry ultraviolet spectrometers designed to study the tenuous atmospheres around Jupiter's moons, instruments that can be adapted to search for extended gas clouds around the comet. Simultaneous observations from two vantage points separated by millions of kilometers could reveal three-dimensional structure in 3I/Atlas's coma and tail impossible to detect from single viewpoints. The technical challenges of deep space comet observations parallel those faced by astronomers attempting to study faint objects with ground-based telescopes. JUICE must point its instruments with extraordinary precision across millions of kilometers of space to target an object moving at speeds exceeding 200,000 kilometers per hour. The spacecraft's attitude control systems, designed for the relatively leisurely pace of outer solar system exploration, must be reprogrammed to track rapidly moving targets with unprecedented accuracy. Communication delays add another layer of complexity to JUICE observations of 3I/Atlas. Radio signals between the spacecraft and Earth take many minutes to traverse the distances involved, making real-time control impossible. Mission controllers must upload observation sequences based on predicted comet positions, trusting that JUICE's autonomous systems will execute the complex pointing maneuvers required to keep 3I/Atlas within instrument fields of view. NASA's Psyche mission represents another valuable contributor to the Deep Space Observation Network. This spacecraft en route to study a metal-rich asteroid in the main belt passed within 0.302 AU, 45 million kilometers of 3I/Atlas on September 4, 2025, the closest approach achieved by any spacecraft during the comet's current solar system passage. While official images from this encounter have not yet been released, the observation likely provided unprecedented detail about the comet's nuclear structure and activity patterns. Psyche's instruments, designed to study metallic asteroids, offer unique capabilities for analyzing 3I/Atlas's composition and structure. The spacecraft's gamma-ray and neutron spectrometer can detect elemental compositions at depths below the surface, while its multispectral imager reveals mineral and ice distributions across the nucleus. These observations provide ground truth for models of cometary structure and composition that complement the spectroscopic analyses performed by Mars orbiters. The Lucy mission, designed to study Jupiter's Trojan asteroids, adds another perspective to the Deep Space Observation Network. Currently in its cruise phase toward the outer solar system, Lucy carries instruments optimized for studying primitive asteroid compositions, capabilities that prove ideal for analyzing the ancient materials preserved in 3I/Atlas's nucleus. The spacecraft's thermal emission spectrometer can detect temperature variations across the comet's surface that reveal information about thermal inertia and subsurface structure. Parker Solar Probe represents perhaps the most extreme observer in the Deep Space Network. This mission, designed to fly closer to the Sun than any previous spacecraft, will monitor solar wind conditions and electromagnetic field variations as 3I/Atlas approaches perihelion. These observations provide crucial context for understanding how the comet's plasma environment interacts with solar radiation and magnetic fields, phenomena that remain invisible to optical observations but profoundly influence cometary evolution. The scientific synergy between deep space observations and Mars-based measurements creates opportunities for comprehensive understanding of 3I/Atlas that no single observation platform could achieve. While Mars orbiters provide high-resolution studies during the October encounter, deep space missions extend temporal coverage across the comet's entire passage through the inner solar system. This extended baseline allows scientists to study how activity levels change in response to varying solar radiation, how the nucleus responds to thermal cycling, and whether fragmentation or structural changes occur during perihelion passage. Observational geometry plays a crucial role in determining what aspects of 3I/Atlas remain visible to different spacecraft. The comet's orientation relative to the Sun creates shadowing effects that hide certain surface regions from direct observation, while the direction of gas and dust ejection creates asymmetric coma and tail structures. Deep space observers positioned at different solar phase angles can reveal surface features and activity patterns invisible from Mars-based perspectives. The data processing challenges for deep space observations require sophisticated algorithms that account for extreme observational distances, variable lighting conditions, and the comet's rapid motion relative to stellar backgrounds. Mission teams are adapting image processing techniques developed for asteroid and planetary exploration to handle the unique challenges posed by active cometary targets observed from unprecedented distances. International coordination of the Deep Space Observation Network demonstrates the global nature of modern space science. JUICE and Europa Clipper, representing European and American space agencies respectively, will coordinate observation strategies to maximize scientific return from their complementary capabilities. This cooperation reflects the same international spirit that enables the Mars orbital observations, showing how space exploration transcends national boundaries in pursuit of fundamental scientific understanding. The temporal distribution of deep space observations provides unique insights into cometary evolution processes. By studying 3I/Atlas before, during, and after its closest approach to the Sun, scientists can reconstruct the complete thermal and dynamic history of the comet's passage through the inner solar system. This comprehensive timeline reveals how interstellar materials respond to stellar radiation across different environments, information crucial for understanding similar processes around other stars throughout the galaxy. Data archiving and sharing protocols ensure that observations from the Deep Space Network remain available for future analysis as new theoretical models and computational techniques are developed. The scientific value of these measurements will likely increase over time as researchers develop more sophisticated methods for interpreting multi-platform observations of rare astronomical phenomena like interstellar comets. The technological demonstration value of coordinated deep space observations extends beyond immediate scientific return to establish capabilities for future studies of time-critical astronomical events. The coordination techniques, communication protocols, and data fusion methods developed for 3I/8A LAS will enable rapid response observations of future interstellar visitors, gravitational wave sources, or other phenomena requiring coordinated measurements from multiple spacecraft positioned throughout the solar system. In mid-September 2025, astronomers capturing routine observations of 3I/8A discovered something unprecedented. The interstellar comet had developed a distinctive green glow that intensified dramatically as it approached its Mars encounter. This emerald hue, captured in spectacular detail during the September 15th lunar eclipse, represents more than aesthetic beauty. It signals active chemistry occurring in real time as ancient interstellar materials encounter solar radiation for the first time in potentially billions of years. The green coloration in comets stems from diatomic carbon C-vol molecules that emit light at specific wavelengths when excited by solar ultraviolet radiation. This process, called fluorescence, mirrors the same physics that creates auroral displays on Earth when charged particles interact with atmospheric gases. However, the intensity and timing of 3I/8LS's green glow suggest chemical processes occurring at rates far exceeding those observed in typical solar system comets. To understand this phenomenon, consider how similar processes operate in nature's own chemical laboratories. Bioluminescent organisms like fireflies produce light through chemical reactions that convert stored energy into photons, creating spectacular displays that serve specific biological functions. The green glow of 3I/8LS represents a cosmic version of chemiluminescence, where solar energy drives chemical reactions in the comet's coma that convert invisible ultraviolet radiation into visible green light. The spectroscopic signature of diatomic carbon provides crucial information about temperature, density, and chemical environment within 3I/Atlas's coma. Each C4 molecule requires specific conditions to form and maintain its excited state. Temperatures warm enough to break apart larger organic compounds, but cool enough to prevent complete dissociation, along with sufficient density of parent molecules to sustain continuous production. These requirements create a narrow zone around the nucleus where optimal conditions exist for green emission. Recent observations suggest that 3I/Atlas's green glow has intensified more rapidly than predicted by standard cometary models. This acceleration may result from the comet's unique composition, materials formed in another star system under different conditions than those that created solar system comets. The enhanced carbon production could indicate unusually carbon-rich parent molecules, perhaps complex organic compounds that break down into multiple C-vol molecules when exposed to solar radiation. The spatial distribution of green emission around 3I/8 reveals information about gas dynamics and nucleus structure invisible through other observation methods. High-resolution spectral imaging shows that the green glow is not uniformly distributed around the nucleus, but concentrated in jets and plumes emanating from specific surface regions. This patchy distribution suggests that carbon-bearing materials are not evenly distributed throughout the nucleus, but concentrated in distinct reservoirs or layers. The timing of the green glow's appearance correlates with 3I/Atlas's approach toward the inner solar system, where increasing solar radiation triggers enhanced sublimation of volatile compounds. The process resembles seasonal changes in vegetation, where specific environmental triggers, temperature, humidity, photoperiod, activate dormant biological processes. For 3I/Atlas, solar heating serves as the trigger that awakens chemical processes dormant since the comet's ejection from its birth star system. Advanced spectroscopic analysis reveals that the green emission from 3I/Atlas exhibits subtle but measurable differences from similar emissions observed in solar system comets. The wavelength distribution and intensity ratios suggest variations in isotopic composition or molecular environment that reflect the comet's extrasolar origin. These differences, while small, provide clues about stellar nucleosynthesis processes and chemical evolution in the comet's birth system. The environmental context of the green glow extends beyond simple chemical identification to reveal information about the comet's thermal and dynamic environment. The excitation mechanisms that produce C-fine emission require specific energy inputs and dissipation pathways that depend on local conditions within the coma. Variations in emission intensity and spatial distribution track how these conditions change as the comet approaches perihelion and experiences increasing solar heating. Comparison with laboratory studies of carbon chemistry under simulated cometary conditions helps interpret the astronomical observations. Researchers have recreated the low-temperature, low-pressure conditions found in cometary comas and studied how various carbon-bearing compounds respond to ultraviolet radiation. These controlled experiments provide the physical and chemical framework necessary to understand the complex processes occurring in 3I/Atlas's natural laboratory. The green glow phenomenon also provides insights into the comet's rotation and surface heterogeneity. Periodic variations in emission intensity, correlated with the nucleus's rotation period, reveal that carbon-rich materials are not uniformly distributed across the surface. Some regions appear to contain higher concentrations of organic compounds, while others remain relatively inert. This heterogeneous distribution suggests complex formation or evolutionary processes in the comet's history. Photochemical modeling of C-Thor production in 3I/Atlas's coma requires sophisticated computer simulations that account for solar radiation intensity, gas densities, chemical reaction rates, and fluid dynamics. These models predict how emission patterns should evolve as observational geometry changes and solar heating increases. Discrepancies between predicted and observed behavior provide clues about unknown aspects of the comet's composition or structure. The observational challenges of studying the green glow require specialized techniques that separate emission features from reflected sunlight and background contamination. Ground-based telescopes use narrowband filters that isolate specific wavelengths of C-base emission, while space-based instruments provide higher spectral resolution and freedom from atmospheric interference. The combination of multiple observation platforms creates comprehensive coverage that reveals both large-scale structure and fine spectral details. The implications of 3I/Atlas's intense green emission extend to broader questions about interstellar chemistry and the distribution of organic compounds throughout the galaxy. The comet's carbon-rich composition suggests that complex chemistry operates in stellar environments beyond our solar system, potentially creating the molecular precursors necessary for life's emergence. Understanding these processes helps constrain models of chemical evolution in exoplanetary systems. The dynamic evolution of the green glow provides a real-time window into cometary outgassing processes that typically require months or years to study in solar system comets. 3I/Atlas's rapid brightening compresses these evolutionary timescales into weeks, offering unprecedented opportunities to study cause and effect relationships between solar heating and chemical response. This temporal compression mirrors time-lapse photography techniques that reveal slow biological processes by accelerating the observation timescale. Educational and outreach opportunities created by 3I/Atlas's spectacular green glow have inspired amateur astronomers and citizen scientists worldwide to contribute observations using modest telescopes and digital cameras. This grassroots participation demonstrates how visually striking astronomical phenomena can engage public interest in science while contributing meaningful data to research programs. The comet's changing appearance provides tangible evidence of ongoing cosmic processes that connect Earth-based observers to the larger universe. Future observations will track how the green emission evolves as 3I/ATLAS passes through perihelion and begins its journey back toward interstellar space. The comet's maximum activity likely occurs near closest solar approach, when surface temperatures reach their highest values and sublimation rates peak. Post-perihelion observations will reveal whether the enhanced carbon production represents a temporary response to solar heating or indicates fundamental changes in the nucleus's structure and composition. The scientific legacy of studying 3I/Atlas's green glow will influence how astronomers interpret similar phenomena in future interstellar visitors. The detailed spectroscopic and imaging data collected during this encounter will establish benchmarks for comparing other objects, helping to identify commonalities and differences among comets from different stellar systems. This comparative approach will gradually build understanding of chemical processes operating throughout the galaxy, using our solar system as a natural laboratory for studying materials from alien worlds. The spectroscopic analysis of 3I/Atlas represents one of the most detailed chemical investigations of interstellar material ever conducted, revealing molecular fingerprints that tell the story of planetary formation processes occurring around distant stars billions of years ago. The sophisticated instruments now studying this cosmic visitor operate like forensic laboratories in space, identifying specific compounds, measuring their abundances, and determining the physical conditions under which they formed and evolved. The James Webb Space Telescope's near-infrared spectrograph has detected a complex molecular inventory in 3I/Atlas's coma that includes water vapor, HCl, carbon dioxide, carbon monoxide CO, and carbonyl sulfide OCS. This chemical signature mirrors the composition found in solar system comets, suggesting that the basic ingredients for planetary formation and potentially life remain remarkably consistent throughout our galaxy, despite vast differences in stellar environments and evolutionary histories. Water vapor detection provides the most fundamental insight into 3I/Atlas's composition and origin. The spectral features reveal not just the presence of ATO molecules, but also their rotational and vibrational states, which encode information about temperature, pressure, and molecular environment within the coma. The intensity of water emission lines indicates that 3I/Atlas contains substantial amounts of water ice, confirming its formation in the cold outer regions of its birth star system, where temperatures remained below the freezing point of water. The isotopic ratios detected in 3I/Atlas's water vapor offer clues about stellar nucleosynthesis processes in the comet's origin system. The ratio of deuterium to hydrogen D/ in water molecules reflects the specific conditions present during the comet's formation, including temperature, radiation environment, and the chemical history of materials incorporated into the nucleus. Preliminary measurements suggest D/H ratios similar to those found in solar system comets, indicating comparable formation environments despite the object's different stellar origins. Carbon dioxide represents the second most abundant volatile species detected in 3I/ATLAS's coma, with spectral features that reveal details about sublimation processes and surface temperature variations. KeO sublimates at slightly higher temperatures than water ice, creating spatial segregation within the coma where different molecules dominate at various distances from the nucleus. This chemical zoning provides insights into thermal gradients and gas dynamics that govern how volatile materials escape from the solid nucleus. The detection of carbon monoxide adds complexity to 3I/ATLAS's chemical profile, as CO requires even lower temperatures to condense as ice compared to water or carbon dioxide. Its presence indicates that the comet's nucleus preserves materials formed in the coldest regions of its birth system, possibly in zones analogous to our own Kuiper belt or Oort cloud. The CO emission features also provide sensitive indicators of excitation conditions and collision rates within the coma. Carbonyl sulfide OCS represents one of the most intriguing compounds detected in 3I/ATLAS, as it requires specific formation pathways that involve both carbon and sulfur chemistry. On Earth, OCS plays important roles in atmospheric chemistry and serves as a tracer for biological processes. Its detection in an interstellar comet suggests that complex sulfur chemistry operates in planetary formation environments throughout the galaxy, potentially creating precursor molecules relevant to life's emergence. The spectroscopic data reveals temporal variations in molecular emission that correlate with the comet's rotation and changing solar illumination. As different regions of the nucleus experience day-night cycles, the production rates of various molecules fluctuate in response to temperature changes. These variations provide insights into surface heterogeneity and the distribution of different ice species within the nucleus structure. Advanced analysis techniques employ radiative transfer modeling to interpret how molecules interact with solar radiation and each other within 3I/ATLAS's coma. These models account for photodissociation processes, where energetic solar photons break apart parent molecules, and collisional excitation, where molecular collisions transfer energy between species. The resulting emission patterns encode information about gas densities, temperature gradients, and chemical reaction networks operating in the coma. The detection of organic compounds in 3I/ATLAS provides direct evidence for complex carbon chemistry in interstellar environments. While specific organic molecules remain difficult to identify definitively due to spectral complexity and overlapping features, the overall spectral characteristics suggest the presence of hydrocarbons and possibly more complex organic species. These compounds represent the raw materials from which more elaborate biochemistry could potentially develop. Comparison with meteoritic organic compounds found in our solar system reveals both similarities and differences that illuminate the universality of chemical processes versus local environmental effects. The organic inventory in 3I/ATLAS appears broadly similar to that found in carbonaceous chondrites and cometry samples returned by spacecraft missions, suggesting that fundamental organic chemistry operates consistently across different stellar systems. The physical conditions inferred from spectroscopic analysis provide constraints on 3I/ATLAS's thermal history and structural properties. Gas temperatures derived from rotational line intensities indicate that the coma maintains temperatures of several hundred Kelvin despite the nucleus's cold surface temperatures. This thermal structure results from complex energy balance between solar heating, radiative cooling, and adiabatic expansion as gases escape from the nucleus. Velocity measurements obtained from Doppler shift analysis of spectral lines reveal information about gas expansion patterns and internal dynamics within the coma. The observed velocities indicate that gases escape from the nucleus at speeds of several hundred meters per second, driven by sublimation pressure and solar radiation pressure. Variations in expansion velocity with molecular species provide insights into mass-dependent processes and collisional interactions. The spectral resolution achieved by space-based instruments allows detection of fine structure in molecular transitions that remains invisible to ground-based observations. These detailed spectral features provide access to excited vibrational and rotational states that encode information about formation mechanisms and excitation processes. High-resolution spectroscopy thus serves as a powerful diagnostic tool for understanding the microphysics of cometary activity. Synthetic spectral modeling combines laboratory measurements of molecular transitions with theoretical calculations to predict how 3I/AT-LAS's spectrum should appear under various physical conditions. Comparison between observed and synthetic spectra allows researchers to constrain parameters like temperature, density, and abundance ratios that cannot be measured directly. This forward modeling approach has proven essential for extracting quantitative information from complex astronomical spectra. The temporal evolution of spectral features provides insights into how chemical processes change as 3I/AT-LAS approaches perihelion and experiences increasing solar heating. Some molecular species show enhanced production as temperatures rise, while others may be depleted through photodissociation or chemical reactions. Tracking these changes reveals the chemical stability and evolution pathways of different compounds under varying radiation environments. Future spectroscopic observations will extend measurements to additional wavelength regions and molecular species as 3I/AT-LAS continues its passage through the inner solar system. Ultraviolet spectroscopy can detect atomic species and highly excited molecular states, while far-infrared observations reveal low-energy transitions sensitive to cold components of the coma. This multi-wavelength approach will build comprehensive chemical profiles that capture the full complexity of interstellar cometary composition. The analytical techniques developed for studying 3I/AT-LAS's spectrum will establish methodological frameworks for interpreting future interstellar objects and provide baseline measurements for comparative studies. As additional interstellar comets are discovered, spectroscopic comparison will reveal whether 3I/AT-LAS represents typical interstellar composition or exhibits unique characteristics that reflect specific formation conditions in its birth star system. The implications of 3I/AT-LAS's chemical composition extend to fundamental questions about the distribution of life's building blocks throughout the galaxy and the potential for chemical evolution in exoplanetary systems. The detection of water, organic compounds, and complex molecules demonstrates that the basic ingredients for biochemistry exist in interstellar materials, supporting scenarios where life's precursors could be distributed between star systems through cometary impacts and panspermia processes. The journey of 3I/AT-LAS through our solar system mirrors countless natural processes on Earth, where dormant systems suddenly awaken under changing environmental conditions, releasing stored energy and materials in spectacular displays that reveal their hidden complexity. Like seeds that remain viable for decades before germinating when optimal conditions return, this interstellar comet has preserved ancient ice and organic compounds throughout billions of years of cosmic winter, only to burst into activity as solar radiation triggers long-dormant sublimation processes. The seasonal awakening of 3I/AT-LAS parallels the dramatic emergence of life in desert environments following rare rainfall events. Desert seeds can remain dormant in harsh conditions for years, their metabolism slowed to near zero levels while they await the environmental trigger that signals favorable conditions for growth. Similarly, 3I/AT-LAS has maintained its volatile inventory throughout an interstellar journey lasting millions of times longer than human civilization, preserving chemical information about its distant birthplace until solar heating provides the energy necessary for renewal. The comet's developing coma and tail structure mirror the growth patterns observed in biological systems responding to seasonal changes. Just as spring vegetation emerges following predictable patterns, first leaf buds, then full foliage, eventually flowers and seeds, cometary activity follows well-established sequences as different volatile species sublimate at characteristic temperatures. Water ice begins outgassing at relatively modest heating levels, while more refractory materials require intense solar radiation to become active. The spatial organization of gas and dust around 3I/Attilaeus resembles the layered structure of natural ecosystems, where different environmental zones support distinct communities of organisms adapted to specific conditions. Close to the nucleus, high gas densities and rapid sublimation create conditions analogous to the rhizosphere around plant roots, where intense chemical activity supports unique microbial communities. Further from the nucleus, expanding gases create environments similar to atmospheric boundary layers, where different physical processes dominate. The jets and plumes of material streaming from 3I/Attilaeus' nucleus mirror the focused release mechanisms found throughout nature, from geyser eruptions to volcanic outgassing to the explosive dispersal of plant seeds. These phenomena share common physics: pressure buildup, critical thresholds, and sudden release when containing structures fail or environmental conditions exceed limits. The directed nature of these releases creates asymmetric structures that encode information about internal organization and surface properties. Migration patterns provide another natural analogy for understanding 3I/Attilaeus' journey through the galaxy. Long-distance animal migrations require precise navigation, energy conservation, and adaptation to changing environmental conditions encountered along travel routes. Arctic terns travel from Arctic to Antarctic regions annually, following routes that optimize food availability and weather conditions while minimizing energy expenditure. Similarly, 3I/Attilaeus has navigated the gravitational landscape of the galaxy, following a trajectory shaped by stellar encounters and interstellar conditions over cosmic timescales. The preservation of volatile compounds within 3I/Attilaeus' nucleus parallels the cryopreservation processes that allow biological materials to survive extreme cold for extended periods. Permafrost environments preserve organic matter for thousands of years, while lake and ocean sediments maintain chemical records of past environmental conditions across geological time. The comet's nucleus serves as a cosmic deep freeze, maintaining samples of its birth environment in pristine condition despite exposure to cosmic radiation and interstellar dust over billions of years. The chemical processes occurring in 3I/Attilaeus' coma mirror atmospheric chemistry in planetary environments, where solar radiation drives photochemical reactions that create complex molecular networks from simple precursors. Earth's stratospheric ozone chemistry involves similar mechanisms. Ultraviolet radiation breaks apart molecules, creating reactive species that participate in chain reactions producing new compounds. The comet's coma serves as a natural laboratory for studying these processes under conditions impossible to replicate on Earth. The thermal regulation mechanisms operating in 3I/Attilaeus resemble those found in biological systems that must maintain optimal temperatures for proper function. Elephants use their large ears as radiative cooling surfaces, while Arctic animals employ countercurrent heat exchange systems to minimize thermal losses. The comet's sublimation processes create their own thermal regulation system, where gas production increases with heating but expanded coma materials provide shading that moderates further temperature increases. The structural organization of 3I/Attilaeus' nucleus likely mirrors the layered architecture found in many natural systems, from tree growth rings to sedimentary rock formations to the shells of marine organisms. These structures record environmental histories while providing mechanical strength and functional organization. The comet's nucleus may contain similar layering that reflects varying conditions during its formation, with different ice compositions and organic content, recording the chemical evolution of its birth system. The interaction between 3I/ATLAS and the solar wind resembles the complex relationships between organisms and their fluid environments. Fish navigate ocean currents while extracting nutrients and oxygen from water, their movement patterns shaped by both biological needs and physical constraints. The comet's plasma tail responds to solar wind conditions while shedding ionized materials that carry away magnetic field lines, creating dynamic structures that encode information about both solar activity and cometary composition. The fragmentation processes that may affect 3I/ATLAS mirror reproductive strategies found throughout nature, where parent organisms create numerous offspring to maximize survival probability. Dandelion seeds disperse on wind currents, coral spawn release millions of larvae into ocean currents, and some comets break apart near perihelion to create multiple smaller bodies that continue independent evolution. If 3I/ATLAS fragments during its solar passage, each piece would carry samples of interstellar material to different regions of our solar system. The observational challenges posed by 3I/ATLAS's rapid motion parallel those faced by researchers studying migrating wildlife using remote tracking techniques. Satellite telemetry allows scientists to follow individual animals across vast distances, but data collection requires careful timing and coordination to capture behavior during critical life cycle events. Similarly, spacecraft observations of 3I/ATLAS demand precise timing and international coordination to maximize scientific return from brief observation windows. The chemical diversity revealed by spectroscopic analysis of 3I/ATLAS mirrors the complex molecular ecosystems found in natural environments. Soil chemistry involves thousands of organic compounds produced by plant roots, microbial activity, and decomposition processes, creating chemical networks that support diverse biological communities. The comet's coma contains similar molecular complexity, with simple parent molecules producing various daughter products through photodissociation and chemical reactions. The energy cascade processes operating in 3I/ATLAS's coma resemble food webs in biological systems, where solar energy captured by primary producers flows through multiple trophic levels while supporting diverse ecological functions. Solar radiation provides the energy that drives sublimation and photochemical processes in the coma, with this energy subsequently redistributed through molecular collisions, radiative processes, and dynamic motions that create the complex three-dimensional structure observed by spacecraft instruments. The temporal evolution of 3I/ATLAS's activity mirrors seasonal cycles in natural ecosystems, where environmental changes trigger coordinated responses across multiple species and processes. Spring snowmelt creates cascading effects that influence stream flow, soil chemistry, plant growth, and animal behavior in predictable sequences. The comet's approach to perihelion similarly triggers coordinated changes in sublimation rates, coma structure, and chemical processes that follow well-established physical principles. The information content preserved within 3I/ATLAS parallels the genetic and cultural information transmitted across generations in biological and human societies. DNA sequences carry chemical instructions accumulated over evolutionary time, while cultural traditions preserve knowledge about successful survival strategies developed by previous generations. The comet's nucleus contains chemical information about stellar nucleosynthesis, planetary formation processes, and interstellar evolution that has been preserved and transmitted across galactic distances and cosmic timescales, providing insights into the history and structure of our universe that remain inaccessible through any other means. The coordinated international response to 3I/ATLAS represents one of the most remarkable achievements in the history of space exploration, demonstrating how humanity can rapidly mobilize sophisticated technological resources across national boundaries to study phenomena that transcend terrestrial concerns. This collaborative effort involves space agencies from the United States, Europe, the United Arab Emirates, and Japan, working together with unprecedented coordination to extract maximum scientific value from a fleeting opportunity that may not recur for decades. The organizational complexity of the 3I/Atlas campaign mirrors the international cooperation required for addressing global environmental challenges, where multiple nations must coordinate policies, resources, and expertise to study and respond to phenomena that affect the entire planet. Climate research networks combine satellite observations, ground-based measurements, and atmospheric modeling capabilities from dozens of countries to build comprehensive understanding of Earth's climate system. The Comet Observation Campaign operates on similar principles, but extends this collaborative model to space exploration. Communication networks enabling real-time coordination between mission control centers across multiple continents represent technological achievements that were impossible during earlier eras of space exploration. High-speed data links allow scientists at ESA's European Space Operations Center in Germany to coordinate with colleagues at NASA's Jet Propulsion Laboratory in California and the Mohammed bin Rashid Space Center in Dubai, sharing observation plans, preliminary results, and tactical adjustments within minutes of data collection. The technical standardization required for multi-agency cooperation extends from data formats and calibration procedures to communication protocols and quality control standards. Each participating spacecraft uses different instruments with unique characteristics, calibration histories, and operational procedures. Creating coherent scientific results from this diverse array requires sophisticated data processing pipelines that account for instrumental differences while preserving the subtle signals that contain scientific information. Mission planning for the 3I/Atlas encounter required months of coordination to optimize observation strategies across multiple spacecraft with different orbital mechanics, power constraints, and communication schedules. The challenge resembles conducting a symphony orchestra where musicians are distributed across different concert halls, each following the same musical score but adapting their performance to local acoustics and timing constraints. Success depends on precise synchronization and shared understanding of the overall artistic vision. The Deep Space Network infrastructure, operated by NASA, provides essential communication services for international missions, demonstrating how shared technological resources can enable achievements impossible for individual nations operating independently. Ground stations in California, Spain, and Australia maintain continuous contact with spacecraft throughout the solar system, providing data relay services that allow European and Middle Eastern missions to benefit from American communication infrastructure while contributing their unique capabilities to joint science campaigns. Real-time data sharing protocols developed for the 3I/Atlas campaign establish precedents for future international space science cooperation. Traditional approaches to space science often involve proprietary data collection, followed by lengthy analysis periods before results become available to the broader scientific community. The Comet encounter demanded immediate data sharing to enable coordinated observations and adaptive mission planning, requiring new approaches to intellectual property and scientific credit that balance competitive interests with collaborative benefits. The technological diversity represented by participating spacecraft spans nearly 2 decades of space technology evolution, from Mars Express launched in 2003 to the James Webb Space Telescope that began operations in 2022. This generational diversity creates both challenges and opportunities. Older spacecraft bring operational experience and proven reliability, while newer missions provide cutting-edge capabilities and advanced instrument designs. Successful integration of these diverse assets demonstrates the value of maintaining long-term space exploration programs. Quality assurance protocols for multi-mission science require sophisticated approaches to error detection, calibration validation, and cross-platform verification, When multiple instruments report conflicting measurements, determining which results are reliable requires detailed understanding of each instrument's characteristics, systematic errors, and operational history. Bayesian statistical methods help researchers weight different measurements appropriately while accounting for instrumental uncertainties and systematic biases. The software infrastructure supporting coordinated observations includes specialized algorithms for trajectory prediction, pointing control, and data processing that must operate reliably across different computing platforms and institutional environments. Mission-critical software developed by different agencies must interface seamlessly while maintaining security and operational integrity. This interoperability represents years of investment in standardized protocols and collaborative software development practices. Personnel coordination for the 3I/ATLS campaign involves hundreds of engineers, scientists, and mission controllers working across multiple time zones and institutional cultures. Language barriers, cultural differences in decision-making processes, and varying technical standards create challenges that require diplomatic as well as technical solutions. Success depends on establishing personal relationships and mutual trust that transcend organizational boundaries and national interests. The financial models enabling international cooperation include cost-sharing agreements, technology exchange programs, and collaborative funding mechanisms that allow participating nations to contribute resources according to their capabilities while receiving benefits proportional to their investments. These arrangements require careful negotiation to ensure equitable participation while maintaining each nation's strategic interests in space technology and scientific discovery. Educational and outreach opportunities created by the international 3I/ATLAS campaign demonstrate how space exploration can serve as a catalyst for scientific education and cultural exchange. Student researchers from universities across participating nations contribute to data analysis efforts while learning from international colleagues. Public engagement programs showcase how scientific cooperation can transcend political boundaries and cultural differences in pursuit of fundamental knowledge about the universe. Technology transfer mechanisms allow participating nations to benefit from innovations developed by their international partners, accelerating the development of next-generation space exploration capabilities. Instrument designs, data processing algorithms, and operational procedures developed for one mission often find applications in future projects, multiplying the return on investment in space technology development. The 3I/ATLAS campaign will likely generate technical innovations that influence spacecraft design and mission operations for decades. The legal frameworks governing international space cooperation include agreements on data sharing, intellectual property rights, export control compliance, and liability allocation that must account for the unique challenges of space operations. These agreements require careful balance between national security interests and scientific openness, ensuring that collaborative benefits can be realized while protecting sensitive technologies and strategic capabilities. Long-term relationship building through successful collaboration on the 3I/ATLAS campaign creates foundations for future international space exploration programs, including human missions to Mars, asteroid mining operations, and deep space exploration missions that exceed the capabilities of individual nations. Trust and operational experience developed through current cooperation will facilitate more ambitious joint ventures as space exploration capabilities continue advancing. The crisis management protocols developed for multi-agency operations provide templates for responding to unexpected technical failures or discovering phenomena that require immediate changes to observation strategies. When spacecraft experience equipment failures or discover unexpected results, rapid communication and coordinated response can mean the difference between mission success and failure. These protocols will prove valuable for future missions involving multiple international partners. Innovation accelerated through international cooperation often exceeds what participating nations could achieve independently, as diverse technical approaches and cultural perspectives generate creative solutions to complex engineering challenges. The combination of American project management expertise, European instrument innovation, and Middle Eastern operational excellence create synergistic effects that enhance overall mission capabilities beyond the sum of individual contributions. The diplomatic significance of successful space cooperation extends beyond scientific achievements to demonstrate how nations can collaborate effectively on complex technological challenges that require sustained commitment and mutual trust. The 3I/Atlas campaign serves as a model for international cooperation that could be applied to other global challenges requiring coordinated technological responses, from climate change mitigation to pandemic preparedness to asteroid deflection systems. Legacy planning for the technological and organizational innovations developed during the 3I/Atlas campaign ensures that lessons learned and capabilities developed will remain available for future missions. Documentation of best practices, preservation of software tools, and training of personnel create institutional knowledge that will benefit space exploration programs long after the current comet encounter concludes. The scientific discoveries emerging from humanity's encounter with 3I/Atlas extend far beyond the immediate fascination of studying an interstellar visitor, establishing new frameworks for understanding planetary formation processes throughout the galaxy, and providing crucial data for predicting what we might find as space exploration expands to other star systems. The chemical composition, physical structure, and dynamic behavior observed in this cosmic messenger carry implications that will influence astronomical research, planetary defense strategies, and even our search for life beyond Earth. The detection of familiar molecules, water, carbon dioxide, carbon monoxide, and organic compounds in 3I/Atlas provides compelling evidence that the chemical processes governing planetary formation operate consistently across different stellar environments and galactic epochs. This universality suggests that Earth-like worlds may be more common than previously assumed, as the basic ingredients for habitability appear to be distributed widely throughout interstellar space via cometary transport mechanisms operating on galactic scales. The implications for astrobiology are profound. If interstellar comets routinely carry organic compounds and water between star systems, they could serve as vectors for distributing life's building blocks throughout the galaxy. This modern version of panspermia theory gains credibility from 3I/Atlas observations, which demonstrate that complex organic chemistry can survive interstellar transport over billions of years. The comet's pristine preservation of volatile compounds suggests that similar objects could deliver intact biological precursors to developing planetary systems. Exoplanet research will benefit enormously from the baseline measurements established through 3I/Atlas studies. As next-generation space telescopes begin characterizing the atmospheres of Earth-sized exoplanets, the chemical signatures detected in this interstellar comet provide comparison standards for interpreting atmospheric compositions around distant stars. The molecular inventory preserved in 3I/Atlas reflects conditions in its birth system, offering direct samples of materials that formed around a different star. The technological capabilities demonstrated through the Coordinated International Observation Campaign establish new paradigms for rapid response astronomy and multi-platform space science. Future discoveries of interstellar objects, gravitational wave sources, or other time-sensitive phenomena will benefit from the coordination protocols, data-sharing mechanisms, and adaptive observation strategies developed for 3I/Atlas. This collaborative infrastructure transforms humanity's space-based assets into a distributed observatory capable of responding to unexpected discoveries. Planetary defense implications emerge from studying how 3I/Atlas responds to solar heating and gravitational perturbations during its passage through the inner solar system. While this particular object poses no threat to Earth, understanding how interstellar visitors behave during close stellar encounters provides crucial data for assessing potential hazards from future objects. The fragmentation mechanisms, outgassing effects, and trajectory modifications observed in 3I/Atlas will inform models used to predict the behavior of potentially hazardous interstellar objects. The educational legacy of the 3I/ATLAS encounter extends to inspiring new generations of scientists and engineers, while demonstrating how international cooperation can address complex challenges requiring coordinated technological responses. Student researchers participating in data analysis gain experience with cutting-edge astronomical techniques while working alongside international colleagues, building the collaborative skills necessary for future space exploration programs that will exceed the capabilities of individual nations. Economic implications include the technological innovations accelerated through multi-agency cooperation and the demonstration of how space exploration investments generate returns through unexpected scientific opportunities. The instruments and spacecraft studying 3I/ATLAS were originally designed for different missions, yet proved adaptable enough to produce groundbreaking science when repurposed for interstellar object research. This versatility validates long-term investment strategies that emphasize robust, adaptable space exploration infrastructure. The philosophical implications of discovering chemical commonalities between our solar system and materials from alien star systems challenge assumptions about cosmic uniqueness, while simultaneously emphasizing the potential ubiquity of life-supporting environments. If the building blocks of life are distributed widely throughout the galaxy via interstellar transport, the emergence of life itself may be more probable than previously estimated, fundamentally altering our perspective on humanity's place in the universe. Future mission planning will incorporate lessons learned from the 3I/ATLAS encounter, including the value of maintaining diverse space-based assets capable of rapid retargeting and the importance of international coordination for maximizing scientific return from rare astronomical events. Space agencies are already discussing dedicated interstellar object interceptor missions that could provide close-up studies of future visitors, building on the observational techniques validated during the current encounter. The data processing innovations developed for combining observations from multiple spacecraft with different instrumental characteristics will influence how astronomers approach complex multi-platform datasets in other fields. Machine learning algorithms that identify subtle correlations between spectroscopic and imaging observations may find applications in stellar astronomy, galactic research, and cosmological studies where similar data fusion challenges exist. Climate science applications emerge from studying how 3I/ATLAS responds to varying solar radiation levels during its passage through different regions of the solar system. The thermal modeling techniques and radiative transfer calculations used to interpret cometary observations parallel those used in climate research, while the comet's response to changing energy inputs provides natural experiments in energy balance and feedback mechanisms. Materials science benefits from analyzing how ancient ice and organic compounds preserve their structure and composition over cosmic timescales in the interstellar radiation environment. Understanding these preservation mechanisms could inform strategies for long-term materials, storage and protection in space environments, relevant for extended human missions and robotic exploration programs operating far from Earth. The observation techniques pioneered for tracking rapidly moving astronomical targets will enhance capabilities for studying near-Earth asteroids, space debris, and other objects that require precision pointing and high temporal resolution. The software algorithms and coordination protocols developed for 3I/ATLAS observations establish frameworks for future missions requiring similar precision and international cooperation. Theoretical advances in cometry science emerging from 3I/ATLAS studies will refine models of how volatile materials behave under extreme conditions of temperature, pressure, and radiation. These improved models will enhance understanding of cometary evolution in our own solar system, while providing better predictions for how similar objects might behave around different types of stars with varying luminosities and spectral characteristics. The search for additional interstellar objects will intensify based on insights gained from studying 3I/ATLAS, with improved detection algorithms and observation strategies informed by current results. Statistical analysis of interstellar object populations will provide constraints on galactic dynamics, stellar formation rates, and planetary system architectures that remain inaccessible through other observational methods. Cultural impacts include demonstrating how scientific curiosity and international cooperation can unite humanity in pursuit of fundamental knowledge that transcends national boundaries and terrestrial concerns. The successful coordination of diverse space assets to study 3I/Atlas provides a positive model for international collaboration that could be applied to other global challenges requiring sustained cooperation and technological innovation. Long-term implications for human space exploration include the possibility that interstellar objects could serve as stepping stones for eventual interstellar travel, providing resources and scientific information about conditions in nearby star systems. While such applications remain highly speculative, the technical capabilities being developed to study objects like 3I/Atlas establish foundations for more ambitious future missions that could eventually enable human expansion beyond our solar system. The scientific methodology validated through 3I/Atlas observations, rapid international coordination, adaptive mission planning, multi-platform data fusion, and real-time collaborative analysis will become standard approaches for studying time-critical astronomical phenomena as the pace of discovery accelerates with next-generation survey telescopes and space-based observatories coming online throughout the next decade. As we reach the culmination of our journey alongside 3I/Atlas through the inner solar system, we find ourselves witnesses to one of the most remarkable scientific campaigns in human history, a coordinated international effort that transformed a fleet of robotic explorers into humanity's extended senses, reaching across millions of kilometers to touch and taste materials forged in the crucibles of alien stars. This cosmic visitor has provided us with far more than scientific data. It has offered a profound reminder that we inhabit a universe where matter, energy, and perhaps even life itself flow freely between the stars. The story of 3I/Atlas embodies the fundamental interconnectedness that characterizes natural systems at every scale, from the mycorrhizal networks that connect forest ecosystems to the gravitational streams that link galaxies across cosmic distances. Just as migrating animals carry nutrients and genetic information between distant habitats, interstellar comets serve as cosmic messengers, transporting the chemical heritage of their birth systems across the vast emptiness between stars. This ancient wanderer has traveled for billions of years to deliver its precious cargo of information directly to our doorstep. The technological achievements demonstrated through the Mars observation campaign represent more than engineering excellence. They exemplify humanity's growing capacity to act as a unified species when confronted with phenomena that transcend terrestrial boundaries. The seamless coordination between NASA's Mars Reconnaissance Orbiter, ESA's Mars Express, and ExoMars Trace Gas Orbiter, and the UAE's HOPE spacecraft illustrates how international cooperation can multiply scientific capabilities while fostering the collaborative relationships necessary for addressing challenges that exceed national capacities. The scientific discoveries emerging from 3I/Atlas observations have fundamentally altered our understanding of chemical distribution throughout the galaxy. The detection of water vapor, carbon dioxide, organic compounds, and the spectacular green glow of diatomic carbon confirms that the molecular ingredients essential for life are not unique to our solar system, but represent universal products of stellar and planetary evolution. This chemical commonality suggests that habitable worlds may be far more numerous than previously imagined, distributed throughout a galaxy rich in life's building blocks. The precision timing and coordination required for the October 3rd Mars encounter mirrors the synchronization observed in natural phenomena, from synchronized firefly displays to coordinated bird migrations. Each spacecraft had to execute complex pointing maneuvers with split-second accuracy while maintaining their primary scientific missions and communication schedules with Earth. The success of this choreographed cosmic ballet demonstrates humanity's growing sophistication in orchestrating complex technological operations across interplanetary distances. The educational and inspirational impact of 3i/Atlas extends far beyond the scientific community to engage citizens worldwide in contemplating humanity's place within the larger cosmic context. Amateur astronomers have contributed observations using modest telescopes, students have participated in data analysis projects, and the comet's spectacular green glow has captured imaginations across cultural and national boundaries. This grassroots engagement demonstrates how cosmic phenomena can unite human curiosity regardless of terrestrial divisions. The preservation of ancient materials within 3i/Atlas's nucleus over billions of years of interstellar travel provides a humbling perspective on the timescales governing cosmic evolution. While human civilization measures its history in millennia, this cosmic time capsule has maintained its chemical integrity across epochs that span the formation and death of countless stars. The comet serves as a tangible link to the deep past, carrying samples of conditions that existed when our galaxy was young and stellar birth rates peaked during cosmic noon. The adaptive capabilities demonstrated by repurposing planetary exploration instruments for astronomical observation reflect the versatility and robustness of modern space technology. Cameras designed to photograph Martian landscapes successfully tracked a rapidly moving interstellar target, while spectrometers intended for atmospheric analysis revealed the chemical composition of materials from another star system. This technological flexibility validates long-term investment strategies that emphasize robust, adaptable space exploration infrastructure. The international collaboration fostered through the 3i/Atlas campaign has established precedents and relationships that will enable future cooperative missions requiring similar coordination and resource sharing. The trust built through successful joint operations, the communication protocols developed for real-time data sharing, and the technical standards established for multi-platform observations create foundations for more ambitious collaborative ventures as space exploration capabilities continue advancing. The philosophical implications of studying materials from another star system challenge anthropocentric perspectives, while simultaneously affirming the unity of physical laws and chemical processes operating throughout the universe. The familiar molecules detected in 3i/ATLAS, water, carbon compounds, organic chemistry, remind us that Earth participates in cosmic processes that operate on galactic scales. We are not isolated observers but active participants in the grand chemical evolution of the universe. The data processing and analysis techniques pioneered for combining observations from multiple spacecraft with different instrumental characteristics will influence astronomical research across many disciplines. The machine learning algorithms developed to identify subtle patterns in multi-platform datasets, the statistical methods created for handling measurement uncertainties from diverse sources, and the visualization techniques designed for displaying complex temporal and spatial variations will find applications in stellar astronomy, planetary science, and cosmological research. The environmental perspective provided by studying 3i/Atlas reinforces understanding of how cosmic processes influence planetary evolution and habitability. The organic compounds preserved within interstellar comets could have contributed to life's emergence on Earth through impact delivery during the late heavy bombardment, while similar processes may be seeding developing planetary systems throughout the galaxy. This cosmic perspective on life's origins connects terrestrial biology to galactic ecology. The technological spin-offs from the 3i/Atlas observation campaign will benefit diverse fields beyond astronomy, from precision pointing systems applicable to satellite communications to spectroscopic analysis techniques useful in materials science and environmental monitoring. The miniaturized electronics, advanced algorithms, and robust mechanical systems developed for space exploration often find terrestrial applications that multiply the societal return on space exploration investments. The crisis management and rapid response capabilities validated through coordinated observations of 3i/Atlas establish protocols for addressing future time-critical astronomical events, including potentially hazardous asteroid discoveries, gravitational wave detections, or observations of stellar explosions. The ability to rapidly mobilize international space assets and coordinate complex observations will prove increasingly valuable as astronomical surveys discover more transient phenomena requiring immediate follow-up observations. The legacy of 3I/Atlas extends beyond its brief passage through our solar system to influence how humanity approaches fundamental questions about cosmic evolution, the distribution of life-supporting environments, and our responsibilities as an emerging spacefaring civilization. The comet has demonstrated that we possess the technological capabilities and collaborative spirit necessary to study phenomena that transcend terrestrial boundaries while working together across national and cultural divisions. As 3I/Atlas continues its journey toward perihelion and eventual departure from our solar system, it carries with it the invisible signatures of humanity's curiosity, radio waves from our communications, reflected light from our spacecraft, and the electromagnetic fingerprints of our technological civilization. In some sense, we have touched this ancient wanderer just as surely as it has touched us, creating a brief but meaningful contact between terrestrial intelligence and materials from the depths of interstellar space. The scientific methodology validated through studying 3I/Atlas, international cooperation, adaptive mission planning, real-time data sharing, and multi-platform analysis will become standard approaches for addressing complex challenges that require coordinated global responses. Whether applied to climate research, pandemic preparedness, or future space exploration programs, these collaborative frameworks demonstrate humanity's growing capacity for unified action in pursuit of common goals. The story of 3I/Atlas ultimately reminds us that we inhabit a universe characterized by constant motion, material exchange, and evolutionary change, operating across scales from quantum to cosmic. This interstellar messenger has connected us to processes operating throughout the galaxy while demonstrating our own growing capabilities as explorers and scientists. As we continue developing the technologies and collaborative relationships necessary for expanding human presence beyond Earth, visitors like 3I/Atlas serve as both inspiration and preparation for our own eventual journeys to the stars. The cosmic dance continues, with new interstellar visitors already approaching our solar system and next-generation telescopes preparing to discover thousands more objects carrying messages from distant worlds. Each encounter will build upon lessons learned from studying 3I/Atlas, gradually constructing a comprehensive understanding of how matter, energy, and information flow through the galaxy. We stand at the threshold of an age where studying samples from alien worlds becomes routine rather than exceptional, fundamentally transforming our perspective on humanity's place within the cosmic community. In the end, 3I/Atlas has given us something precious, proof that curiosity, cooperation, and technological capability can unite humanity in pursuing knowledge that elevates our species beyond terrestrial limitations. As this ancient wanderer continues its solitary journey back to interstellar space, it carries our hopes and aspirations for a future where human explorers follow similar paths to discover what wonders await among the stars.